Good morning, everyone. My name is Shaurya Rahul Narlankam. I'm a PhD scholar here at Sustra Lab, so the Sustainable Transitions Lab, here in the Department of Management Studies at IISc. I'd like to welcome you all to the IDEEA Open Source Model Dissemination Workshop, which is also organized by Sustra Lab in association with the Environmental Defense Fund, SusPoT, and IIT Roorkee. So IDEEA stands for Indian Zero Carbon Energy Pathways, right? In its essence, it's an open source dynamic engineering economic model which is designed to reduce the cost of an energy system required to meet a particular energy demand. So the model does so by first quantifying the amount of energy and energy sources available to the system, and by also accommodating the various processes to produce, store, transport, and transform them by recognizing the technological processes to do so through the use of very simple real life parameters like efficiency and cost. The model has the ability to combine these technological processes to form technology chains to produce to convert the energy sources to the required energy to meet the demand, right? So ultimately what the model is doing is that it's comparing various technology chains that it is forming and producing a least cost option that meets the requirements and constraints imposed on the system. So through this workshop we hope to give you a brief overview of the model, its applicability in various sectors, a basic workshop on the use of the model, and also do some capacity building in the open source community. So now I'll hand over the presentation to Mr. Shamrit Sharma, PhD scholar at Sustra Labs and IISc at IISc, to take you through the next session of the workshop.
Thank you, Rahul, for the warm introduction. I, on the behalf of Sustra Lab, under the guidance and leadership of Dr. Balchandra Patil and the entire IDEEA team, welcome you all to this dissemination workshop. The open source model, energy model, attempts to stimulate and visualize electricity system. Visualizing the system open up a wide range of possibilities. It empowers user to test the system without physical installation and thereby design, debug, rationalize, calibrate, or even reimagine the entire system. As you must be aware, we across the globe are now heading towards an era of green energy, and electricity systems across the world are transitioning from the traditional thermal dominated system to greener alternatives like solar and wind. This transition on one hand would ensure sustenance of resources for our future generation, and on the other hand would reduce the harmful emissions associated with the electricity sector. Intrigued by this phenomenon and to investigate the various modalities of this transition on the Indian electricity sector, Environmental Defense Fund, Indian Institute of Science and Jadavpur University joined hands to develop this indigenous open source energy modeling, IDEEA, that is Indian Zero Carbon Energy Pathways. This model primarily emphasizes on the economic rationalization of generation portfolio and can be used to study implication of various levels of energy system transition. We published our preliminary findings in one of the top rated journals last year. It also gives me immense pleasure to share that we have successfully presented our work across the globe, for example in the US, Thailand and Kolkata in the past year, and got generous appreciation for it. The model has now reached its final stage, which has been possible with the guidance from the mentors of IISc and our collaborating partners. Taking one step further, we present the model and its finding to the most distinguished achievers in this field today. I thank you all for accepting our invitation and coming to this workshop. Now, I would like to invite the main pillars of the IDEEA initiative onto DS. Mr. Partha Basu from EDF, Dr. Balchandra Patil from IISc, and Dr. Tarun Sharma from IIT Roorkee. First, I would like to introduce Mr. Partha Basu, a lead India advisor to Environmental Defense Fund, directs US aid-funded Clean Air Catalyst, a multi-stakeholder consortium working towards clean air in Indore and developing a protocol on hyper-local hotspots in India. Has 2 decades of experience in vehicular emission, and during his formative years, he contributed to developing PUC at the Society of Indian Automobile Manufacturers. His stint in UN partnership, Clean Air Asia for air pollution in India, started as India representative to India director and then to South Asia liaison. He was a part of working group on non-motorized transport promotion at the Ministry of Urban Development and developed the world's first walkability survey app. He partnered with the Ministry of Heavy Industries and NITI Aayog to reduce emission and improve freight efficiencies with the introduction to structuring the country's first and only green logistic working group. He also launched the Air Repository of Indigenous Air Quality Studies with NWERI and CPCB. In short, he has a plethora of impressive work. Now, without further ado.
Today morning I was discussing with Professor Patil, exactly a couple of years back, 3 years back, we were in this room and we wanted to start something like this, where we bring together modelers who can work on their own on developing something which they think is a plausible way of energy efficiency. And we wanted to give modelers that freedom to choose their own pathways and design their own pathways. And today we are back in this room, and we are very happy with this journey that has taken so far. But still, there are a lot of milestones to achieve. There was a time when people, there were patients who will go to the doctor and they will say, "Doctor, I'm unwell. And what do you think is wrong with me?" The doctor will say, "You ask too many questions. I'll give you the medicine, you'll be fine." And over a period of time, we got patients who just went to the doctor and said, "Doctor, I'm unwell. Please fix me. I don't want to know what's wrong with me." And now you have patients who actually want to know what's wrong with them, and the doctor will also explain. So the energy modeling timeline has been more or less similar. There was a time when I am assuming the policymakers wanted to know how models work, but for decades they were told that this is how models work, and you do not have to ask more questions. We'll just give you you just give us the assumptions and we'll give you the results. But today, I'm hoping that we will get into that room, into that situation where policymakers would really want to know what kind of assumptions go into making those predictions and those results that we are forming, and is it possible for us to change those? And that's what we wanted to achieve through this journey. I've been tasked with introducing IDEEA. Samrit, can you press the next? I'm sorry, it's not working. Thanks. I will just talk a bit about us. We are Environmental Defense Fund. We started in 1960s, and environment has been our core, as the name suggests. And the idea was generated by a group of people who noticed that the osprey, or basically the bald eagle, which is a symbol of US emblems that you can keep seeing in CIA and all Hollywood movies, they were getting extinct prematurely, and it was basically because of thinning of the shells due to DDT. And a group of people got together and started working with them in order to prevent this, and the first lawsuit was filed and DDT was banned in the US. And that's how a group of people came together, raised money, and called themselves the Environmental Defense Fund. We are not exactly a funding organization. We are very much an NGO, a group of 1,500 odd people who are mostly doctors, economists, and lawyers. But very soon we realized that the onus of protecting the environment does not lie only with the government or with the society. The industries play a very important role as well. And that's how we started working with the government and the industry. So 1970 onwards, we started working full-fledgedly with the industries. Most of our pioneering work has been with FedEx, the Cokes, the Pepsis, the Volvos, and the many other such companies, the Amazons and the McDonald's as well. So people like Arnold Schwarzenegger, the mayor, was the governor at one point of time, worked with us in basically introducing lead-free fuel in California, and so far and so on. Perfect. Thanks. This is where we are spread. There are a few more other points where we are working currently, and just to give you a glimpse of how our scientific hunger is, how much of our scientific hunger is. So we work a lot on GHG and predominantly on methane, and we have been working on methane since almost a decade now, and we were trying to look at methane emissions not only from the oil and gas sector, which is very obvious, but we also look at many other sectors, including the households, because in many parts of colder countries, methane is used also for warming houses. So we also wanted to measure them, and we got into a point where we felt that this kind of hyperlocal measurement getting into blocks and industries is not possible. We will never be able to complete the globe like this. And in 2018 we decided that we will launch our own satellite. So because of COVID, we are running late by almost 7-8 months. So we are now likely to be launching it end of this year in October. So this is Fred Krupp, the CEO of EDF, who's announcing the launch of MethaneSat, and that is exactly how the methane satellite looks like. So IDEEA, when we wanted to work, we have been working on energy modeling, as I said, for a very long time, and we developed a model scaffold, a structure which we felt was very helpful in allowing people to design models on them, and we wanted to see whether India will be up for it. And we went into various meetings with various Niti Ayogs and the likes of it, and many other government institutions, and we found that there were a set of group of people who would be there in each meeting room represent the modeling community, and we wanted to understand, is the modeling community that much? And then we did a landscape work. In fact, Lavanya led that work, and we found that there are more than 40 organizations in India who actually understand and work on energy modeling, but they are never representative because they never attend those meetings in government, in government meetings, the high-level meetings organized by them. So we wanted to create this platform where the energy modelers from across the country, from various universities, industries, etc., come together and work on them and feel free to develop something on their own. And that's how this original genesis of IDEEA started. We launched this in July, and that's when the 3 organizations, and I'm grateful to Indian Institute of Science and Jadavpur got together, and we launched, and we coined this name. I'm sorry, it doesn't exactly rhyme the way it should be. It should be something like IZCEP, and we know it didn't rhyme, so we called it IDEEA. We picked up letters from the name, and it turned out beautiful because it started appearing in small write-ups, and we did a couple of work. So this is our goal. We wanted to create a community. And I am very happy to say that you could be the first joinee of those community of trained in energy modelers in the country, and to create and enable this open platform, open energy modeling platform and environment to engage in India's journey towards the net zero, because we have a goal, and this goal cannot be fulfilled sitting in a room. We have to work with all sectors, all kind of industries. The decarbonization, if India has to meet that goal, actually it needs support from all 360-degree sectors, and that's why creating this community of modelers from different industries, different sectors becomes very, very important. So this is more or less our objective, but I would let Professor Patil talk about it more as one of the key founders of the initiative. And this is the group. Some of them are already in the room, and I would urge you all to kindly clap with me to cheer all of them. Thank you very much. Thank you, Professor Patil. Thank you.
Thank you, sir, for giving a brief overview of the project. Now, I would like to introduce the pillar and a Yoda of Sustra Lab, our mentor, Dr. Balchandra Patil. He has molded and given direction to many young and bright minds of IISc. He is ranked among India's top 10 management researchers and first in strategic management. He is ranked among the top 2% of energy scientists in the world. He has 35 years of experience as a faculty at IISc and visiting expert at Harvard, UNDP Bangkok, AIT Bangkok, and IGIDR Mumbai. He has investigated 48 research and consultancy assignments for organizations like UNDP, European Commission, World Bank, TERI, SIDA, SNEI, RCUK, IGIDR, DST, other government and private organizations. He has expertise in energy and environmental economics and policy, sustainability energy aspects, and energy system planning and modeling. He has authored 6 books, published 150 papers in international and national journals and conferences, and edited books with H-index of 26. Last but not the least, he has also been conferred with the Distinguished Alum Award of Manipal University in 2011. With such a stalwart of work, I would no longer waste his time, and let me call Professor Dr. Balachandra Patil to discuss open source model.
Yeah, basically I want to express kind of an happiness, that we have made a good beginning. As Mr. Partha said, idea of IDEEA is to create a platform or establish a platform of energy researchers, energy modelers, energy analysts. The challenge what we not exactly faced, what we observed was, we became too comfortable using black box energy models, supplied by someone, either proprietary or commercial, not much of open access. And we are happy to, input lots of data and get out something, which are difficult to interpret, difficult to understand, how such results we have obtained. No answers for all those things. I think we wanted to come out of that, the whole process. Can we open the black box? Can we simplify the whole process? And try to have our own indigenous, as Mr. Partha aptly put it, set of energy modelers who can help not only the government at large for long-term, medium-term, short-term planning of the energy system transition, or even other sectors, non-energy as well as non-electricity sectors. Even industries, if we can provide a flexible platform where everyone can play a role, depending on their organizational interest or individual interest, and from a start, develop multiple set of models, either tweak into the model, adapt to their requirements, or add on to set of maybe constraints, equations to expand the model, make it really complicated so that, it would be nice to work with complicated system, but not as a black box. Open it, understand, then implement. I think that was the idea. And as Mr. Partha said, this collaboration started sometime during, I think, peak COVID time. We wanted to have good number of physical meetings, but fortunately, we minimized cost of travel, contributing to again reducing our carbon footprint. Most of the meetings happened online. I think off late we have started. I think this is the second physical meeting we are having. I think this whole process itself has contributed towards achieving a small aspect of zero carbon transition. And in terms of hard work, this is the last 2.5 years of work. And in addition to community building, we also had objectives like research, then stakeholder engagement. A good number of stakeholders, they do not want to do modeling. They don't want to do any analysis. They are happy with the findings, or kind of sensitization. We also need to engage with those kind of stakeholders, policy makers, bureaucrats. At the end of the day, they are going to use these results and findings, implement. Again, my second argument, ad hoc policy making is dangerous, evidence-based, or informed policy making is always good for the country. And models, help us to do, not only for the country, even for the business or the corporate sector. Historically, there used to be an argument, an experienced manager is much, much better than a trained analyst. But now things have changed because, databases have become now big data. and experience doesn't help in understanding that voluminous data. I think one has to be a good analyst. That's why I think now the benefit has come to youngsters who are trained modelers, trained analysts, in with respect to various kinds of tool. I think this is another thing. When I said researcher, our focus was long-term advanced research. I think we, in addition to other collaborators of this whole program, we are together, I think, training about 6 PhD scholars. I think 4 of them are here. No. Yeah. No, I am not putting you under energy modeling. Okay, anyway. The 4 of them are there. I think Tarun, are you? Yeah. And Jadavpur University, the 3rd collaborator, they are also training 2 PhD scholars. The significance of this is we are giving to the nation 6 new energy modelers who are well trained, who have spent significant amount of time in learning, understanding and doing research around that. And Dr. Tarun, again, he was my student. He is a pre-IDEA energy modeler, but he is now contributing significantly in terms of expanding, developing this whole effort. And as Mr. Partha said, this collaboration is with EDF. Dr. Oleg Lugawai, who is where is this? Yeah, in the 2nd row, the last but one, who was kind of a trained modeler, I think, who gave the initial training to all the young team members. He is also into now global dissemination of this effort. I think with about 50 plus participants across Asia Pacific, South America, and this whole program is happening online. I think that effort is becoming significant because there is recognition for a need for this kind of expertise. And we also focused on publications, then capacity building. One of the first events is this one. I am seeing good number of unfamiliar faces, which is very useful and happy thing for us. We can expect more people joining this energy, I would say, not only modeling, energy analyst community. And I think I don't want to take too much of the useful time. One more comment I want to make. See, what typically we see is the stage is full of people like me, grey-haired, old. Now I think it is time to for all seniors to take the back seat, the last bench of the auditorium, and give the stage to the youngsters. The world is transforming, like our energy system. We are moving away from significant traditional old-style technologies to modern, unpredictable, uncertain, dynamic, renewable energy. That has created significant new challenges. I don't think that can be solved by people who are untrained in modeling, untrained in all these tools. And it's difficult to train the senior people. I think the demand is for youngsters, people like you, and you have to take the higher stage. So I am making that beginning, this is kind of my personal argument also. Let us go to the last bench, and give, otherwise, we will never, typically, I think that is the practice. We never want to give that stage to the younger generation, unless they need to wait till, or they should stop coloring their hair so that, they look and take the center stage. And I am giving that stage to you. I think next, Dr. Tarun would be telling more about the open access energy modeling and kind of exposure he had. The next to the
Very young, dynamic, budding professor from IIT Roorkee, Assistant Professor Dr. Tarun Sharma. He received BTech in Mechanical Engineering from NIT Hamirpur and did his MS and PhD from IISc. He received the the Best Thesis Award for his PhD work in benchmarking and modeling the sustainability transition of the Indian electricity system. He is a recipient of an Impact Postdoctoral Fellowship from the Chinese University of Hong Kong, where he worked for 18 months. He was a postdoc fellow at Energy Policy and Modeling Group, University College Cork for 2 years. He also worked as an assistant professor of operations management at the Institute of Rural Management, Anand, Gujarat for 6 months. He received TAD Wise Fellow and was second in order of merit for his batch. He published his work in several leading journals and conferences like Applied Energy, Energy Policy, and International Energy Week. He has expertise in energy modeling and policy, sustainability transition, and applied operations research. His ongoing research focuses on the development and maintenance of a suite of analytical models such as optimization, agent-based models, and their applications to answer questions related to energy transition. So without further ado, I would like to call Dr. Tarun Sharma.
Good morning, everyone. Thank you for the kind introduction. So I'm Tarun, and first of all, I welcome you all to this workshop. And I'll be speaking on the open source modeling and its opportunities for India. So this is where I come from. So it's in the state of Uttarakhand, North India. That's the main building for IIT Roorkee. And so to begin with, I state, bases the research and application in the area of energy, that there's a need, requirement, and the potential to nudge activities, decisions, and choices of actors all along the energy system to ensure desirable outcomes. So there is the understanding. It began with, say, the early oil crisis which happened, that we need to do something about how energy is consumed, transported, or produced for that matter, and to make these changes to a certain end. Some of the themes related to these actions and outcomes are mitigation of climate change. So we know energy is one of the main contributors to the climate change. So we want to mitigate that. So we want to do something about it. We want to plan the system at the least cost to have high reliability. And that includes generation expansion, energy efficiency, and other things. We want to develop and deploy advanced technologies, electric vehicles, carbon capture storage, maybe electrify mobility, maybe whatnot. And this in turn is going to require actions and collaboration, not just from the government, not just from one business, not just from academia, but probably a shared understanding and all of them coming together to build a strategy, to act. And of course, policy landscaping by industry stakeholders and think tanks to come to a shared understanding that this is what we want to achieve. This is who needs to do what and at what timelines. And of course, there is a lot of business opportunity in this. It's here to stay for the upcoming decades. So this is in my mind, the primary context why we do energy modeling, why we bother about it. So with this as the background, that we need to understand what the energy system is, who all are involved, and what they need to do. So this is the first step. So now next, what is energy system? So energy, we all understand, is ability to do work. We understand it as, say, heat, work, governed by laws of thermodynamics. And there's a complex network of, intersecting supply chains. And this is one snapshot. So if you look at the geographic spread, the temporal spread of this picture, so it's a global network essentially, and the dynamics is happening, say, your electricity is getting synchronized at 50 hertz at a frequency of 50 hertz per second, right? And then some things are happening, say, exploration of oil, coal, they take multiple decades. So there's all this dynamics happening in the energy system. And of course, it involves action by government. There are new entities, new entrepreneurs coming into the picture, big businesses there. So all those extremes we see in this. The spatial extent is large, temporal extent, the business is small, large, government actors, state, center. So all those are somewhere there in this picture. And what is happening globally? So to just to tell you, so say if we look at how energy consumption has changed across the world over past few decades, so it's an upward going curve. And why? Because we know energy is a necessary factor input for economic activity. It is directly correlated to Human Development Index. So that is why we consume energy. And of course, there is huge heterogeneity across, say, the major geographic blocks. So say India is here, and China is here, and we see the rise from here onwards. It's been quite stark. So that is where the major geographic blocks are in terms of energy. And of course, we can break it down, look at fuels. So we have oil, coal, gas. So it was biomass earlier, if you go maybe a century back, then coal came into picture, then oil, then substituted by gas. And currently then we have wind and solar as well. So it's a complex mix, and it's small, but nonetheless we hope that it makes it takes a bit more share going forward. And of course, it does not come without externalities. So externality is something which is outside of the main transaction. So we have emissions. So CO2 is one of the main sort of elephant in the room. So we have pollutants as well and other things which are maybe equally important. But nonetheless, for the moment, I'll focus on CO2 emissions. So collectively, all over the world, we are emitting, say, close to 35 gigatons. And we know from IPCC that at the current rate, we probably, so it's roughly 500 gigatons equates to 1 degree Celsius rise. So at that rate, we have, say, maybe a decade. And there's a lot of alarm all over the world, and not just the governments, civil society, businesses. So a lot of them are committed for zero carbon and whatnot, right? So it's a serious problem. And again, the responsibility and the ownership for action, it varies. So India per capita is very, very low, but collectively we are a responsible country, so we want to do something about it. So we don't want to go down the path which the other countries did. And here's the same information just in terms of gradients. So how, say, the year on year, how the changes have been happening. And we see signatures of, say, all the major world events, be it the 1970 crisis, the 2008-9 crises, again, which did not impact us that much, but in the West had significant implications. And again, once again, the key themes of the actions and the consequences. So again, climate change, mitigation, renewable integration, pollution abatement, electrified mobility. So they're all big ideas, complex ideas, would take action from lots of people. This is, again, so this is the general sketch of, say, energy, why it's important to this realization that we need to do something about it, and how do we go about harnessing that potential, and specifically India. So India is another word in the title of my talk. So I have to talk specifically about what's happening in India, what is the opportunity for India. So this is a nightlight image of India from a decade back, but I like to show it, but maybe now it's even more brightly lit. And again, the spatial extent, so all these power generators are spread all across the geography of India. And there is some of the dynamics related to, again, the emission of CO2, SO2, which associates with all the generators across the expanse of India. And I make a comparison with China, because that's a fair comparison, comparable size and population. So in terms of SOx emissions, so there's a very stark reduction for China. For India, it's an upward going thing, so it's a concern. And similarly for CO2 emissions, we have a concern. And then again, on the supply side of things, we have a reduction in capacity utilization. So essentially what I'm trying to say is, so all the issues relating to energy, they are known, understood globally, and we have them in India as well. So that is why in India also we need to do something about them. And again, going forward, we have then promises of, say, deploying large amounts of renewable, or say, reducing our carbon intensity by a certain percentage point relative to 2005 base year. So all those things are there going forward, and they are here to stay. We know that much. So again, this is the same slide which I put initially, that there's a need and requirement to nudge activities in the energy sector. And from last 50 years of research and practice in this area, we know that we can actually do something about it, to nudge the players, or maybe the influence, the choices and the decisions made by businesses, made by governments, to then steer the system in the desirable direction. And some of the actions and themes are here. So assertion, next I'm making a claim that energy modeling is indispensable. So all these things are important, now we understand that. And we've also understood that they are important for India as well. Energy modeling is indispensable for addressing these needs and harnessing this potential. So what is energy modeling? So first I just show a use case. So this is a projection of, say, electricity mix for India for the upcoming decades. So currently we are somewhere here. So we have a number or a set of numbers for 2025, 2030, 2040. Here is just some historic data, again, say where we have come from, and this is where we are likely to go. So this plot is from International Energy Agency. So it's, I think all of you would know, because I assume you're all working in the area of energy. So that's the big think tank, OECD think tank. So might we wonder, how do they arrive at these numbers? First of all, we all agree that it's important to have some projection. So if you're navigating, we need to have a map as to where do we go next. And collectively, that too, when we're navigating such a large supply chain, lots of intersecting supply chains, that too. So we need to have a roadmap, right, where to go. So, and this is one example of such a roadmap. And then the next question is, how do they come up with these numbers? And why do all people tend to believe them? So all of the people will quote them. We also, in our research, quote these numbers. So this is at the back end what happens. So this kind of analysis, this kind of roadmap is brought to life through what we call energy modeling. And energy modeling in terms of equations, this is a snapshot from one of my own works. So typically you'll have, say, you're capturing all the information about the system, the diverse supply chains, and we use, say, algebraic optimization modeling for those of you who are familiar. And you'll have, say, multiple sets with multiple indices and whatnot. And eventually you'll have a set of equations, the equations running into millions. And you'll have something like this. So if you want to algebraically render it, and it's okay, you don't need to bother about what they represent, but just to showcase what the underlying modeling means in terms of equations. And again, I can render the same information. So earlier, the supply chain network I showed was a very simple one, an aggregate one. So we had just one block for, say, a set of activities. So here it's for a system of a small size, say 5-6 million people. So all the small yellow dots are each individual technologies. And then this is a network interconnecting them. That's the actual energy network. So this is how it looks like when you actually model it in the system. So this is a rendering of that supply chain network. And this, again, here just to showcase what energy modeling means. So again, this is what you need to scan. This is what you need to look carefully at. What is happening, what is going to happen where, and where is it that we need to pay attention to. And yeah, other ways, then you have the equations, you have the underlying network, and the results usually get represented like this. And the earlier stacked chart from IEEA, which I showed you, which was projecting the capacity mix for India in the upcoming years and decades. So this is another way of rendering this information. So these Sankey diagrams. So again, if you're referring, say, India energy statistics, so every year they'll make a Sankey diagram of where we are currently. So we essentially map that in a lot of detail and then make a projection into future, and then be able to look and make statements about what's likely to happen. Going forward, how we are going to consume electricity, where is it going to come from, how we are going to heat our homes, how we are going to be moving around. So mobility, is that going to be hydrogen-based, electric-based, or whatnot? So then we are able to sort of make these plots. And of course, energy modeling is an entire continuum. So Professor Balachandra already mentioned that the various individual entities might have interests, say generation expansion, dispatch optimization, sourcing. Sourcing is one of the key things, I think, for businesses, efficiency, and that also figures with ESG as well. So it's an entire continuum. Say, yeah, this again is the technical domain from electric engineering, but then this is the domain in which especially we operate, and energy system optimization comes all the way here. So IDEEA currently is here. So we have production cost simulations as well as capacity planning. And then going forward, we want to sort of, we already have plans to do this as well. And why am I speaking to you? Why am I invited to be here? So I was already introduced. I have some experience, spent some few years working on these things in Europe as well as in Hong Kong. And I personally have published in those areas. So I've done economic dispatch, unit commitment, production cost, and a lot of it under the guidance of Professor Balachandra during my PhD days here. Yeah. Okay, and after having done this, so we understand the problem is important, something needs to be done about it. The second assertion was that energy modeling is indispensable. That is the tool. What energy modeling involves, the underlying equations, how the network could be visualized, and what kind of outputs then in turn come from value chain. Again, latest lithium find, again, that has so many repercussions for the entire energy transition. So you can begin to do that kind of work after you have this. So this work is prereq for that. And developing an innovation system, and again, as I mentioned, so the things are going to require action from multiple stakeholders, and it's going to require, it will have elements of research, development, and deployment. So that in turn is facilitated through this. And essentially, we have a platform for integrating models and scenario development. And the thing essentially is we are unlocking the potential in research as well as industry through this exercise. So again, the story thus far. So I've convinced you, I've tried to convince you that energy and the systems that provision it are important and they're complex. Energy modeling provides a systematic way to map the energy systems and project their future states under various scenarios, assumptions and conditions. Energy modeling is indispensable for nudging activities, decisions and choices of actors all along the energy system to ensure desirable outcomes in India as it is everywhere in the world. We have seen how the equations look like at the back end. We have seen how the underlying supply chain network looks like. So what's next? So there's another word, open source, in my title. So we've spoken about modeling. So now I come to the open source bit. And for that, we first look at the pipeline. What is the workflow? What is the workflow in the energy modeling? So we have, again, it's similar to any kind of analytical exercise, be it machine learning or anything. So we begin with some raw data. We need to do some pre-processing, some formatting, or some data handling. Then process that data, make a modeling instance, then deploy results. And again, results require processing because energy modeling, so a typical result for a model of reasonable size will probably have 500,000 data points. So it's no mean task to visualize. So the visuals which you've seen earlier, so they're made by processing say 500,000 data points in an Excel sheet. So it's no mean task. It's not trivial at all. So, and then interpretation. So that's the entire modeling pipeline. And again, basis some of this analysis, the decisions will be made about, say, investments which are large. So say a coal power plant is 5 crore per megawatt and similar numbers for all the technologies. So all these investments are massive, right? So you need to pay enough attention to the details as to how these things are done. And this is where the next critical point in my mind, as per me, is. So essentially this optimization modeling, it's prescriptive. So again, those of you who work in this area, say as compared to regression or any machine learning kind of paradigm, so this is different. So say in machine learning, you have a LHS, left-hand side, right-hand side. You divide your data set into training, testing, validation. So you have a loop. You have a measure of how good the fit is, to what extent there's a bias, and to what extent you're able to sort of on a new data, which the model has not seen before, how good or bad it does on that. Against that, of course, on the back end in the machine learning, you also do some optimization to estimate the parameters. But here, we don't do that. Here we have an optimization formulation. There's no RHS as such. We only have the LHS. So essentially modeling whatever we know about, say, the system state and the interrelationships between them. So the energy balance, so capacity constraints, which are known facts. So we take those as given, and then we simulate the operation of the system, and then employ constraints like carbon budget, or say certain fraction of energy from renewables. It's a different, it's a different workflow altogether. So the validation is the key word. So with any kind of knowledge system, we need a way to find out if the knowledge coming out, to what extent can we trust. So in the machine learning, we have a framework for that. But what do we have here? And especially when there's so many high stakes riding on it. Right? So this is where sort of this open source thing comes into picture in a very, very big way. So essentially, we're not comfortable if say government is making decisions based on some black box. Nobody else knows how do they come to the conclusion that they arrived at. Right? So we're not comfortable with it. Simply, it's not, we just cannot manage with that. It's simply not agreeable to us. So what essentially happens in the domain, again, people have been working on these things for half a century now. So what tends to happen, again, from the international experience as well, people tend to develop the source code, the data pipelines in an open source setting. So what that essentially allows for scrutiny by multiple people. So anybody can look up, pinpoint a fault, recreate the analysis for themselves, especially, of course, it's a skill job. It requires, it's a full-fledged job to do this. But nonetheless, there's that possibility is there. And that in turn then begets trust and stakeholder buy-in, because that's the most critical part. So you want everybody to come to a shared understanding. This is collectively what we're going to do, and then they can sort of on their own find out what's the best thing for them to do as a business, as a think tank, as academia, or whatnot. So this is sort of the experience, how things have been happening elsewhere as well. So again, this is not unique to India. So similar to that, there's IDEEA is the initiative, which we are trying to do an indigenous effort in India. And open code and open data, allowing for maximum scrutiny, allowing for replicability, and as a consequence, stakeholder buy-in and probably more effective action. So it is in this sense that the open source energy modeling is unlocking the potential in research as well as in research academia as well as in industry as well. Okay, so what are the other consequences of doing it open source? So it minimizes the time of development and application of a reference energy system or say bottom-up model. So CEP here is a capacity expansion planning. And reduce duplication of efforts. So everybody need not, because it's a massive effort to get the model up, to get the equations in place, have it checked. So everybody need not do it. So if there is sufficient trust that n number of people have already checked it, then not everybody needs to recreate or say reinvent the wheel in some sense, right? So they can take it as given. And it frees up time and money to develop new ideas. It boosts learning curve in energy modeling, because otherwise it's a quite an intensive, it's a very specialized skill-based job otherwise. So not many people can do this otherwise. So it improves transparency, reproducibility, credibility, and understanding of energy models, which lead to better research and policy advice instead of black box. So that is what it is positioned as an alternative to. And of course, if we have open source, then it comes with it has its own merits. So it improves quality through feedback and correction. It facilitates a collaboration, because essentially, again, we talk of sectoral coupling or whatnot. So you're going to require data and whatnot from so many different people. And if every time you have to do, say, non-disclosure agreement or whatnot, then you spend a lot of time. You need a person, multiple years spent on that only. So if everything is an open source and sort of we can start asking governments also, different departments, to put their data in open source, then it sort of facilitates collaboration on the things which actually matter. Making reproducible research accessible and integration with other models and software, and can increase public acceptance of difficult infrastructure trade-offs, because that's always a worry, right? With nuclear power plants as well, and so many other things. With so many say these infrastructure things, be it a road, be it a transmission line. So, but essentially, if we can collectively come to an understanding this is what we need, what is needed, then probably there's not too much resistance to it. So here enters IDEEA. So the mission is to build a community of trained energy modelers using an open access modeling framework for engagement in larger energy policy discussions nationally and globally. And these are the aims. You've already looked at it, so I'll just flash this slide. And here again, it's the same slide again. So having done all this, so these are the takeaways. So we hope to achieve these things. So I'll not repeat them again, but this was the slide again. So the story thus far. The open source energy modeling offers opportunities for India. So I hope I've convinced you to some extent, and of course I'm here through the day. So we will continue to talk throughout the day. So what's next? So create awareness and interest in energy modeling community, a capacity building of potential energy modelers to showcase the advantage of open source modeling, building linkages with the industries, think tanks, and the public sector, and then reinvent and continue to work on how IDEEA model could be relevant in the present policy landscape. And this is very close with the question, how can you engage?
All the speakers for their talk. So before we go to the next section, we'll, which is for the basic workshop on the use of the model, we'll break for tea, which is assembled upstairs, and we'll collect back here at 11:30. But before we break for tea, we would like to request all of you to come on stage for a group photo, and then we'll disperse for tea and collect back around 11:30. Thank you.
Yeah, so good morning, everyone. And so finally we start the actual session of the workshop, where we'll kind of give you a total overview of the IDEEA model, like where we started from and what were the objectives. Then we'll give a brief algebraic formulation of the model, and finally we'll explain the code. So the story starts with climate change. Like the story of renewable energy transition itself starts with climate change. So because of the climate change and its associated problems, worldwide there is a move towards transformation towards renewable energy. But why this renewable energy sector or the electricity sector? That's because electricity sector is one of the highest contributors to the global GHG emissions. And this is the sector where the results can be obtained the fastest. The decarbonization efforts, if deployed in this sector, will yield the fastest result. That's why the world leaders, they have kind of chosen this as the priority area, and they are moving towards it. So India also has given some ambitious targets in various international platforms. So with the current generation mix of India and the expected generation mix going forward, what we see is the proportion of coal right now is huge. And we and the Indian power system experts in general, we are used to handling coal systems. Renewable is pretty new. As in, when we are introducing more and more renewables, we are being aware of its challenges and the shortcomings and the issues associated with it. So instead of putting in renewable first in the system, then finding out the problems and then finding a solution, the better way would be to deploy a modeling approach. So we model the system with the desired proportion of renewables, see how it works, and then go forward with it. So as of now, with the coal system, the generation side was more or less deterministic. We knew that, okay, if we have a 100 megawatt coal power plant, we'll get around 95 megawatt of generation. Or we can vary it. We can, if we want, we can get 50 megawatt. If we want, we can ramp it up to 80, whatever. But in case of renewables, that is not the thing. That is the biggest challenge of such a setup. So we are transitioning from a static supply, and demand is always variable. We cannot determine how much the demand would be. So from a static supply variable demand system, we are moving to a variable demand and variable supply system. So that creates a huge challenge. Briefly we have put the various challenges of this transition, and to study these we need modeling. So power sector projects, they have huge investments and long gestation periods. Like money invested today would give you results 10 years later. So with such an uncertain, huge investment system, it is advisable that we are very sure of what we are doing, where we are investing. So that's where we need a modeling approach. So we need to have a robust forecasting mechanism where we exactly visualize what is going to happen in future, how the future looks like, and then look at all the modalities. So with these in mind, we developed this, as was explained in the morning sessions, India Zero Carbon Energy Pathways, or the IDEEA model, with the objective of achieving balance of dynamic demand, dynamic supply, and tracking the growth of the low carbon or the zero carbon transition efforts. So this is the basic overview of the model. So we started with an algebraic formulation where we designed the objective function and the constraints in a typical mathematical operation research format, and then we translated it into a code. So the code comprises basically an optimization model in GAMS, and we use RStudio to provide the inputs to the GAMS model. And then with the model we have preliminary results, we validate with an existing system, and then once validated, we fine tune if required, and then finally we come up with different scenarios of extent of renewable penetration and so on. So coming to the mathematical model, as I've already said, or as shown by Tarun in a snapshot, it's a very similar thing. We have a typical linear programming problem. So linear programming basically is, it has an objective function, that is the overall objective of the exercise, based on or subjected to certain constraints. So the objective function is very simple. We want to minimize the total cost. I mean, ultimately economics is also important. So we want to minimize the total cost, which comprises of investment cost, O&M cost, the fuel cost, cost of unmet supply, and the exchange cost, that is cost of trading. So investment cost, O&M cost, and fuel cost are pretty self-explanatory. The cost of unserved supply, that is kind of a penalty which we have done. So in a cost minimization model or any cost minimization exercise, the easiest option is to just not supply. That will minimize your cost. But that's not a desirable thing. So that's why we have kept a penalty. This is a dummy cost, which is a penalty for not supplying, so that the model doesn't explore that option. So this cost minimization is subject to certain constraints. Constraint as in, firstly we have generation limits, like each technology has its own limits for generation. As I said, thermal can generate up to 95%, whereas a solar power plant would go up to only 25% of its installed capacity. So such peculiarities of each generating technology is given as one constraint. Next is the available capacity or the available potential. It's not that we can install solar or wind plants wherever we want, how much ever we want. It depends on the natural resource. So that's a constraint. Next is the ramp rate. This is more applicable in case of thermal plants. And of course, yes, we have demand. That is the overall guiding factor, I would say, that we have to meet the demand at all times. And again, neither go overboard, neither excess generation nor under generation. Next, we have put a provision for battery storage. So that's still not popular, but yeah, we have explored that option as well in our model. So we have included both battery storage as well as reservoir storage. And finally, the unserved load constraint, as I've mentioned earlier. So I will just give you a glimpse of a few equations that we have considered in each of these constraints, and then we'll go to the code. So just to give a flavor of what the mathematical model looks like, and then we'll show how we have translated into the coding language. So these are the sets and indices or the variables used. Okay, I'm skipping this, and so are the parameters. So these are basically the variables of the algebraic model. So first, as I had mentioned, generation limit constraint. So thermal generation, for example, it is limited within the installed capacity multiplied by a generation factor, that is maxima and minima. We have a technical minimum for thermal plants, and we have a technical maximum. So we have constrained the thermal generation between these two limits. Similarly, the approach for solar is a little different, because that depends on the solar irradiation available at a particular location. We have integrated our model with GIS mapping, which we'll explain during the coding session. The solar generation is basically again constrained by the maximum and minimum possible irradiation at that location. Similarly, capacity constraints. So we have capacity available, we have new capacity, and the retired capacity. So the available capacity is something in between installed and retired. I mean, the net of installed and retired and previous existing capacity. Then we have put ramp rates as constraints, where the output from outtake is nothing but the output from a generating technology. So it is constrained between the ramp up and ramp down rates of that particular technology. The subscript T stands for technology. And then we have demand, so where the total generation from all sources should be greater than equal to demand. So basically demand needs to be fulfilled all the time. Why is it greater than equal to? Because solar and wind we don't have control. So at times there can be excess generation. But it should not be less than at any point of time. And next we have the emission constraint. We have put constraints on how much emissions we can afford. And this is the storage which I was talking about. So we have, this is basically reservoir storage. We have any excess generation would go into storage, and at the time of under generation, storage would supply power. And the unserved load is defined as this: if it is equal to demand minus the sum of output and storage output, like output from generating technologies and the output from storage. So if that falls short of demand, we have unserved load. So then we'll proceed to the computational formulation, where we'll show you how these equations have been translated in the programming language. So I request Samrit to take over from here.
Thank you, Abhishek. So there are three types of modeling approach. So first is mathematical modeling, where you are modeling your equations, algebraic equations. Second is computational, where you are developing algorithms to run those equations in an iterative fashion. Third is the physical models, which we will not be discussing, but here we'll be showing the link between algebraic model and the computational model. So the software we are using R, and the optimization tool we are using GAMS, and the solver we are using CBC. So the solver, what it solves the equations which have been given in the GAMS. That's the purpose of the solver. Okay. You can also program in Python, and solver you can use Gorby for this GAMS software, GAMS programming, where the algebraic equations are put. Then comes the software requirement. Energy RT, as discussed, is a reference energy system where all the function classes, GAMS equations are being stored, declared and defined, right? So it's a capacity expansion model, and or it's a bottom up. So we are under the classification of energy economics. So there are two types of energy modeling. One is process modeling. Second is energy economics model. So in process, you optimize the thermodynamic cycles and chemical reaction, but in economic models, you are optimizing the operational side of decision making and economic, right? And then in economic energy economics model, there are other the further bifurcation are top-down model and bottom-up models. So in bottom-up, you can model from regional to national level. So it's a homogeneous modeling. So you intersectoral it won't be done, but in top-down you can have a intersectoral modeling too. Intersectoral as in from electricity to transport, if there is a feedback required, that you can do in top down, but not in bottom up, right? Then comes the second, irregularly date. So it is the package to handle your date and time queries. So if you want to change or convert your date and time to date or month or year, you'll be handling through the irregularly date library. Then comes a table where it presents the data frame in a tidy manner. Then comes the SF. So SF is basically a library which we use for GIS data handling. So there are two types of there are two forms of library, like SF and SP. SF is special features of geospatial data handling, and SP is spatial polygon for spatial polygon geographic vector data, right? Then comes ggplot. Basically, it's a library to plot your GIS data. Same goes for the ggRepel too. It's a basically a label zone for ggplot only. Avoid overlapping of text. Then come SP depth. Basically, it gives its spatial weight matrix and provide polygon contingencies, right? So basically, in this model, what we are using SP depth for is to calculate the neighboring states in GIS data. Then comes the GDX RRW. So it's an interface between R and GAMS. So it whatever the R inputs into the GAMS is relayed from GDX RRW. So what you do when you install R and GAMS, you you install GDX RRW, and then you initialize the path of GDX RRW to GAMS. That's how we connect R through GAMS. Then I will show you the overall approach of this model. So first, what are the inputs in the model? We are doing GIS data of Karnataka. You can enter, we have given a provision for you can enter the other states also, or there can be multiple states at one time also. Then we are plugging in the Karnataka load curve, which you can get from open, you can source it from open sites on internet, or you can find it in, from SLTCs of a particular state. Then comes the weather data. So in weather data, we are using MERA2 data. The MERA2 is basically modern era retrospective analysis for research and application. So what it does, it's a geographical atmospheric reanalyzed data from NASA. So it contains at least 41 years of data from 1982 till September 2020. So it contains weather data, as in it contains wind speed, atmospheric pressures, density, precipitation, and solar radiation, which we'll be using in the model. Then comes the install capacity. As an input, we are keeping a technology. So you must have seen the capacity constraint. So we are plugging in the capacities of each technology through, and this you can get from the sites, or the CA report, or you can get it from other KPT similar sites. Then you enter the ramp up, ramp down rate, technical minimum of coal plants. These are the operational constraints which we have entered. Then comes the early generation and interstate exchange. So why we need this input, because here today we will be discussing validation. So when you model, you actually validate whether it's true or not. For this purpose, we have used the actual data of 2019, right? So this data consists of generation hourly for a year from different power plants of different source, like coal, solar, wind, all these sources. You got 8760 data points. Then come the economic cost of each generating technology. So as discussed by Abhishek, you can get there is an input for investment cost, O&M cost, fuel cost, and then again a dummy cost for unserved load. These are the inputs will be doing in the code. Then what does the model do? The model estimate or models the solar wind generation from weather data. So for example, for in wind you got speed, but that doesn't translate to power. So you need to convert those wind speed into power curves. Then again for solar you get given solar radiation. So you'll be converting into that power form of equation. Then comes estimate hydro generation from change in reservoir levels. So what we have done, we're modeling hydro power with the reservoir level. So the reservoir will have input, flow, discharge, or equivalent energy throughout the year for 8760 data points. So we'll be modeling that. Then comes balance demand with thermal generation subject to ramp up, ramp down rates, and technical minima. Basically, what it means is, if since we are going to renewable, or we are transitioning to zero carbon, so if the capacity is not enough, or right, so what we do, the model will take then ultimately the thermal. So this is how we will balance the supply and demand. So this will be the last option if no renewable is available at that time. Since we all know, okay, solar and wind are very variable and intermittent source of generation. And then comes solving the LP to minimize overall costs, which we have all seen in the objective function. Then what are the outputs we'll be generating today? So we'll be showing like optimal fuel mix over the minimizing overall cost. So what is the optimal cost for the system while choosing the renewable energy, right? And then we'll be comparing the actual versus model. So the model one will give you the optimal generation, least economic cost, system cost for that year or even model year. So what we have provided, we are also modeling for future years. Through milestone years, you can project to 20, whatever year you target, like 2040, 2050. And then we'll be simulating scenarios like if you want only renewables to be generating, so you'll be using only renewables. If you want storage to come into the picture, you'll be simulating through storage also as a balancing technology. Again, the data has been taken, weather data from NERA2, KPTSL and C reports have been, from that we have taken installed capacity, operational constraints also. Yes, KERC and CERC, we have taken costs from those reports. And energy RT, again, it's an energy referenced system which we are using. Okay, now this is this flow, how we have built the model on R. So basically first step is to acquire data and then clean it. So this is the hardest part. You getting data from different sources, you assimilate, you compile those data, and we have taken data from different power plants, right? So those sheets, the data is spread across 365 days to 24 hours. But those data are like in a very dispersed manner. So like in day shift and night shift, so we have to collate those data and then we aggregate those plants into according to the sources. So like if one plant and two plants are from thermal and the third plant is solar, so that's how we have aggregated the power plants. Then comes the loading the libraries. Whatever the libraries will be needing in the coding, we will load that libraries. Then comes the GIS coordinator. This we have taken from the open source. You can download from internet. And choose the GIS, whatever the location you want to choose in that coding. Time resolution, we have used 1 hour for demand, for supply. And then classifying early generation data. As I said, we have aggregated the data according to the sources. Then comes and plugging in the early demand data. Obviously, it's a clean data, processed. Then comes raw data of pre-processing raw data of NASA. So what we are doing, we are collecting the weather data. So it's a huge file, it's 350 GB file. And it's all stored in FST format compressed. So you need to solve that thing because it is a huge, it's taking a huge size. Then comes cleaning the data. Then what you are doing, in cleaning and preparation the data, basically you are modeling the data. So you are converting wind speed or solar radiation to the power generation. Right. Then comes you merging your weather data according to their geolocation. So at Karnataka, at particular latitude, longitude will be getting a different generation from as compared to the other latitude and longitude. So this along with the latitude and longitude for 365 days, 24/7, you'll be getting those data.
In this solar system, when we consider the thing, so are we considering the tracking system also, like one axle tracking or two axle tracking?
So we have looked at that. There is a provision. There is a provision. You can use different type of technology like tracking, dual tracking. We have used here fixed tilted.
Seasonal tracking only you are using?
Yeah, no, so it's fixed, it's not tracking anything, it's a fixed solar panel. But there is a provision, you can use all these technologies also. So there is a command for that. In the back end, there is a keyword to use that. That will also be described in when we come out with the manual. We'll tell what all technologies are available. You can do that also. Yeah.
Any any kind of technology like waste to energy technology, nuclear energy, anything can be.
Yes. So what you do, we have defined the classes. So in those classes, whatever the parameters you want to enter according to that technology, you can enter that, and then you can enter in this R code. So you yourself can code that. We'll show you how to do it, what are the keywords where you can enter, what parameters you need to enter. I'll discuss all this during the code.
So whatever new technology you want, you can just create a chunk for that and define the parameters. So we'll show the sample ones which we have. Already new technology you can easily have.
Out of curiosity, I ask.
Oh, sure.
So what is the modeling unit at what we are modeling? Are we modeling for the state?
You can model.
As I said, you can model for the region, like Karnataka here we are discussing, you can model for India also. So yeah.
Model it for one building.
Yeah.
Model it for multiple countries.
Yeah. So you can model at a plant level, power plant level, you can model it to your own building.
Unit of modeling could be
Anything. From micro to macro, you can do modeling anywhere.
Okay, and the output would look like what is the mix of.
Yeah. So Varun will be discussing some case study. He'll tell you how to do that.
Did you do any case study on island type of environment? So for example, Mumbai.
Exactly, we have done everything, but let us.
Not everything.
No one. So I will explain you.
Later we'll discuss all these case studies also. I'll tell you. Don't worry.
I mean, we hope your question will be answered.
I have a modeling related question. Any specific reason we are not considering the starting of cost for generators or anything?
So we are working on a macro level system. So such micro details you can add it. The starting cost. So whatever cost we have considered, the generation cost, it's like inclusive of all that.
Because it's economic model, right?
Yes.
That's why. Okay. But we are not considering, just for clarification. We are so far it's not developed.
The startup cost you mean?
Yeah.
So that's a part of the fuel cost you measure. In the beginning you need oil, right? Fuel oil. So it's a part of the fuel cost.
If you have non-linear generation and if you give a time span of 1 hour, how good will it able to give the result?
See, right now we have not worked on what you are saying is for one or we have considered the aggregate system.
Okay, it's for non-linear generation. If it's a non-linear generation, it's contributing maximum to the system.
When we have a system of many power plants, that gets evened out. Non-linear generation of one power plant, the starting phase you need, or it gets averaged out when we have a lot of plants in the system.
For example, if you take a microgrid, you have renewables contributing more. Then coming to
that is taken care of by the RAM rate.
And then in that case, if you have modeling time span is 1 hour it will take, then linear programming model will exist.
Absolutely.
We have taken the aggregate, our modeling granular, the resolution of the model is 1 hour. So whatever generation is 1 hour, the
generation itself is not linear. It may be seconds or it could be hours or minutes also.
That's what the resolution is 1 hour. So we have averaged it over 1 hour. If there is a variation between 1 hour and the next hour, that we have considered. The average of this hour, the average of that hour is equal to that. So to predict the generation, the pattern of generation, we have used the NASA's data.
I think so. We will continue after this session.
So
Let's
these
see
details,
what all are there. Then we can go for questions. Before that, what all are there? If I say also in the air, you won't be understanding why it is being implemented. Let us see what is there, and then we will go. So.
Okay. So first we'll be loading energy RT. As I said, it's a energy reference system. It contains all the equation, classes, function, which we'll be calling on R. So it contains of functions and classes. You're not getting. Zoom.
Code, control, plus minus. Oh, outline जो है ना, माउस नहीं है तेरा.
So here we'll be coding. This is a console, and here you will get the environment variable, whatever the declared one we are executing. Like the first we'll be uploading your energy RT. We'll be checking whether it's updated or not, right? Then we'll be loading libraries. As discussed earlier, we are loading energy RT, lubricate table. All these functions will be, these library will be used later in the code. Okay, now the solver. Solver we are using CBC. So first you'll run this solver, and then we have given the option for CBC and Cplex, so, but here we are using CBC. So if you want to use Cplex, you can unhash the solver Cplex and hash the CBC solver. But we have used CBC, right? So we'll run this, and then we'll save on source. Basically, it's saving the GAMS path and all onto the R code. Then we'll run the source solver option. Again, we have given we are declaring making a file folder for figures where all the figures will be stored. Then comes the scenarios simulation folder, and then temporary file for storing all the miscellaneous results. Again, as I discussed, you can enter the time zone according to your specification, and here we are using Kolkata time zone, I mean Indian time zone. Then comes the base year. So for validation, we are using base year 2019. Why? Because this is a pre-COVID year. There was no disruption of supply and demand. That's why we are using 2019 data. Then you can use. Then we are entering model base year. So what you can do, you can model the model years to next 5 years also. So I'll show you. Just a minute. So what it does, the model can take next 5 years also. So now if you want to check model years, yeah, so if I want to check how many years it's taking, I've taken from 2019 plus 6 years. So what it does, the models till 2024. This is one option. You can also model through milestone years, which we have defined later in the model, which Varun will be explaining. Okay, this is how you do the model years. Then come the weather year. So here for validation, we are using 2019 data, but you can also take the previous. So we'll be using historical data of weather year. So what we do, we take the historical data for like previous 5 years, or you want to 1 year, 2, 3 previous years, and then it extrapolate to the future years also when we for future scenarios. So for here 2019, but if you want the previous years also, you can do this by unhashing this line, and you'll get the future years too. Sorry, previous years. So if we check how many years it's containing, weather years, from 2019 to 2014 to 2019, right? So since we are discussing only the 2019, we'll hash it. Now we have given the option of conversion of currencies. So for you can convert it to from rupees to your US dollars also. Okay, so I'll run this chunk. Okay, next is the data input for GIS. So whatever data, so we are plugging in the data of GIS information data. You can take it from open source on net and load it and convert into art data and then load it. So it's a plugin provision we have given. And then comes select region. So if here we have entered Karnataka, so because we have the actual data for Karnataka, that's why we are using Karnataka. Otherwise you can enter this as a vector. You can enter any other state. Right. So here we select like two data, two states. Wait. Oh wait, it's a small c. Okay, so now we have entered two states. So it will be selecting two states now. As you can see here in the map, since your console for this is big, you can't see in the map. But yeah, you have selected two states here in red, like Karnataka and Tamil Nadu. Wait. Okay, we can't zoom it. Okay, then I am again we have the data for Karnataka only, so we'll be reverting back to Karnataka only. So we are also showing or commenting on where you can input your data. So the plots will be stored in the figures file also, and is being showed here also. So I will show you what this GIS data, what it does it contain. What does the actual GIS data look like? Right, so it will contains it is a class special polygon. As I said, there are two data frames. Spatial polygon is stored in the form of spatial polygon. You will have the state's name, their locations also. So yeah, so these are the regions like Andaman, like West Bengal, Odisha, Andhra Pradesh. Okay, so these are the short form given here. Then comes you are just calculating or estimating who are the neighbors for a state. The next comes the center of the region. This helps in estimating what is the area of that region. So this is stored as a data frame which contains the name and the area of that region. All the data frame classes will be shown in the global environment. You can check it here. For example, this region area. You can see for Karnataka, the area kilometer here declared. So this is your GIS plugin. This is how it will be changing. You are only plugging in the data, and then you can change accordingly what region you want to focus. Then comes the time resolution. This is a provision we have done for to convert the date and time to day and slice. So if you want to refer to day and slice, you can. So we have provided functions like date time to time slice day and hour. So I'll show you the how to do it. So this function we convert to day and hour. So you have chosen here is the date for 1st January 0th hour. So this is how it will be shown. So this, why we needed this is just for plotting, because since the date and time takes too much space, we have use a day and hour for time representation. Then we are loading the generating capacity. So this data has been taken from the website, CEA website. So what does the data look like? So if you want to see the data, not change in the code, you can write on the console of R. This is how the data looks like. Biomass 2019 was 134 megawatt. The generation was done this, and then again availability. This is how you do. If you want to select the year also, you can select the year also here. You want to select if you want to select like a particular source. So what you can enter the data frame, like GenCap is the data frame here, right? And then you can index it for like first row and the third column. If you want to change this capacity, you can change it also. We've given that command also. Then comes the generation by R. So after assimilation, cleaning the data and aggregating the data, we'll plug in this data into this chunk. Right. Then comes the reservoir operation data. As I said, we'll be modeling hydro for with the reservoir data. Again, these are data available on website online. Then we load the load curves hourly for 365 days. So the load data consists data from it's from 2010 to 2019. Right, from 2010 to 2020, sorry. So if you want to select, what you can do, you can filter the data by just selecting this function, load data frame, and then indexing to load year, and equating which year you want. You put the year and then comma, then all the columns you want, you can do that also. For example, I'll show you. So for example, I want 2019 data. I've entered 2019 data for the rows, and then I want all the columns, right? So my data now looks like, so how would I check how many years I have in this data? Again, through unique. Okay, now we have selected 2019 data. Now comes the weather year. So again, I reiterate, we have taken data from MERA 2 data, and how we have model, I'll tell you. So for wind speed, we have got at 10 meter, we got wind speed, and we got wind speed at 50 meter in Mera data. So how would you model for 120 or 100 meter? That's one thing we'll be modeling. So what we do is, like, since we'll be using Hellman's constant expression, where V1 upon V2 equal to H1 upon H2 raised to power Hellman's constant. So we'll calculate the Hellman constant, and based on that distribution of Hellman's constant at each and every time of the year, 1 hour time slice year, and at each every location this will be different. So after that we'll extrapolate the wind speed to 100 to 120 meters to 200 meters using Hellman's constant. After that we'll be using power curve to determine what is the power generated at that particular time, at that particular period. So this is how at different hub heights you can get a different wind power curve. And for solar radiation, we'll get the shortwave incident data. So what we do, so what we are modeling is we calculate the nominal total irradiance, which is a summation of beam irradiance, ground reflected radiance, and sky diffuse irradiance. We are not calculating shading area and all. It's just a nominal solar irradiance. Again, then you enter the again this data is hourly and location wise. So every location, like the grid resolution is 0.625 into 0.5 resolution of longitude and latitude. In kilometers it would be 60 into 50 kilometers. So the grid size of each spatial location will be like that. Okay. So now we have wind technologies. Now we are selecting the wind technology. So we have selected 120 meter class, and now so certain potential we will have at every slice. So how much of that is used depends on the turbine you are using, right? So if 15% of that potential is being used, 20%, 25%, 30%, so you can select that data by this line target. You will be targeting one. Based on the turbine, you can use whatever potential percent you want to use. So here we are using 35%. Okay, again the solar, the same, we have modeled that into total nominal total irradiance. Okay, now we'll build the weather classes, where the weather data, whatever potential power you have modeled, that will be put into the weather classes. So here we have chosen 120 meter hub height wind for wind. So you can use 50 meter also. Here you can choose whatever in your data it's shown, whatever hub height you want, you can choose here. And then according to that you can you choose the technology, right? So this is 120 meter hub height potential generated of wind, and red dot shows the installed capacities of wind. Okay, now you are making a repository, because why this repository, we are accumulating, or we are defining this into repository. Later these repository will be called in the model. So this is a neat way, tidy way of doing coding. Okay, now we have made a weather wind class. So some of you were asking how would you model this. So this is a keyword. If any other renewable energy which depends on natural resources, you can model it through new weather. You can put all the specification, you want to put the unit, how much the slice as in you want hourly data or annual data you want to model, right? And then you want to put the weather model data in the form of data frame into that class, right? So here the weather data dot frame, you will here enter the data for particular year for each slice, and whatever W value is weather, it's a weather potential only. Whatever you have calculated, solar total irradiance and wind power. So new weather is a class which is mentioned in energy RT, and through that you can enter any other natural resource data after modeling that particular renewable energy. Then comes the solar. So what we have done, there was some variation. So what we have done, we'll calculate an adjustment coefficient where we have the actual generation data from the KPT cell, and we have estimated some solar potential. So we have got the adjustment coefficient, which will be multiplying to the projecting one, so that somewhat it matches the actual generation solar curve. Again, we have with the new weather, we will be classifying this solar chunk with the new weather classes, and then you will be entering those potential in there, whatever specification you want, R unit, whatever you have given. It's very important you enter the unit also, because for the uniformity. Right, then comes year and slice, and then the weather value. Weather value is again the same, whatever you have modeled in solar, you'll get that potential. Okay, then comes the hydro reservoir. So we have reservoir data, the inflow, outflow, equivalent energy it contains slice wise throughout the year. Slice wise as in hourly data for 365 days. So this is how the data looks like. You have discharge, equivalent energy inflow at a particular day at a particular hour. Again, you will be converting these resources into classes, so that they are being called later in the model. Again, here we are converting this through a keyword new weather. You can model the resource, enter the values of those in equivalent energy of hydro storage. So what we have kept, the capacity of storage is equivalent to maximum equivalent energy throughout the year. So whatever is the maximum is the capacity of the hydro reservoir. Okay, now here comes the main part, which all you will be asking, like what all technology you can enter. So this is generating technology. So what all technology we have used? Thermal, solar, wind, hydro and all. But if you want to enter any other technology, you can do that also. Again, through a keyword here, new technology. This is a keyword here, as in this is a class named enter in energy RT. So through this you can enter any technology. Now your question is, you want to model through plant level. You can do that also. You do this through this new technology only. So but here, yeah.
I have a question continuation. When you said we can model at plant level, what about this grid size? The grid size is flexible to choose, or it will
No, so the grid size is fixed. Mera data has 0.625 into 0.5.
Then plant level will not make that sense.
Yeah, so that's what.
The grid size is fixed since we have used
Mera data. So you can, if you want.
Use any other database, you can verify. I mean, the grid
So
size
how
will be
comfortable it is to switch across this data
We
set
show it in
versus the data source?
So if you want a different, so Mera data comes with the fixed grid size.
Right.
So if
He'll tell you how to switch data
Okay,
sources.
all right. Looking forward.
so if you want to change, then you have to again plug in the different data sets there only, in the weather data only.
I think we are
So it's the centering of one line that's
Yeah.
comfortable.
Yeah.
Rest of the code, no need.
No need to change. It takes into that whatever grid size you have taken in the initial in the metadata, it's the same. So for you, if it's a very different grid resolution, you can take that. There's no need to change in the between, because if the data is coming along with the grid resolution, you don't need to enter anything.
Yeah, makes sense. Thanks.
So here we will be entering for thermal, right? So what all parameters you are entering? For thermal is like again the new keyword, new technology. You enter the name of the technology, description. It's a coal based technology. Input, commodities. So commodities basically for every technology, commodity input output would be different. So output for any technology is electricity. Input for thermal is coal, or you can put diesel also, whatever your specification is. And it enters, there is a provision also, auxiliary commodity you can also enter. If the commodity with electricity or with the power generation, you have heat or gas also as an auxiliary, you can enter that also. So as a keyword, there is an aux commodity is given, you can add that also. You can group those commodities also. There is a provision also given, you group those commodity like yeah, so you can do that, and then you enter the unit of the commodity, and then here what we are doing, we are not modeling combustion and all chemical reaction, but here you can model, if anybody has a intricate data, you can enter the combustion percentage also, but we are only modeling electricity here, so we will not be entering any combustion percentage, so we have kept it 100% here. Again, the output we are given is electricity, the unit. Then capacity to actualize, basically for how many time slice or how many days this will be active. So that then you can enter the commodity effectiveness, as in commodity input to use, basically conversion, coal conversion efficiency. You can enter this also. Intermediate efficiencies, like if you want to enter the from electrical efficiency, you can do that also. So here is a, so think of this as a box. Coal is entering in this and you are getting electricity. So if you want some intermediary efficiencies also to be entered, operational efficiency, you can enter to this also. And then again, if you want to limit your generation for a slice wise, as in every hourly, if you want to limit that generation, you can limit. Like here we have put 0.2. Right, and if you want to put annual constraint on annual generation, you can do through AFS. So we have given timely, through timely resolution also, like 1 hour you can limit also, or you can annually limit the generation. Right, then again ramp up, ramp down, we've given hours. Then we enter the cost. Whatever the cost is, you can convert also. Cost you will get from the tariff reports, O&M cost, you can enter investment cost, right? Then comes the capacity, which is already there. So if I'm modeling for future year, so how much capacity I needed, what is already installed. So I'll be showing this as a stock. So whatever is installed already, will not be modeling or investing on that. We are not done that. So what we do, whatever the current installed capacity in 2019, we enter through stock, we enter that, and then you can also reduce your capacity generation throughout the year. So for example, 2019 it's 10 megawatt, the is your capacity. 2040 you want till 7 megawatt. So you can reduce that also if you want to. If you want to reduce the percentage of generation, percentage of capacity to generate, right? So for where do you do that? Where do you reduce? Here is the option. You can, here it's 0.7. You can enter 0 also. So by 2040, your stock will not be, your installed capacity will not be generating at all. Then comes the option of at what time of the year you will be investing. Start investing. So 2019, like for example, if you want to add no capacity, you want to use the existing technology, So you will hash it. You will start of the ending, you will not mention, or end of the investment, you will not mention it, right? But if you want to start the investment from 2020, so you will enter, like here it's end, you can write start equal to list, comma, start equal to 2020, right? And then if you want to invest till 2040, you can write the end till 2040. So it will be investing till 2040. Then comes the operational life, 25 years. And again, slice is R. Hourly, so what option is given? Either you have slice hourly or you have annually. Then again we will, like for hydro, the same procedure. You enter the name of the technology. Before mentioning any technology, you enter through new technology is the keyword, the class, right? And then you enter the region, input, like water, hydro is used. There is no combustion, you write it 0, right? Output is electricity. Then how much you want to limit slice wise, right? Lower limit you put 0.1. As per your specification, you can put any you can input here. So again, these are all classes classes with a predefined parameters. So whatever you don't want, you hash it. Okay, then you enter the O&M cost, investment cost. Again, the stock, you enter the installed capacity of the current year, and we are not degrading the generation of the capacity for hydro. There is that option also. So we have shown you with in thermal we are degrading the output of the thermal source, but in hydro we are not. So there is two options, you can do that also. Again, the solar, you enter the solar technology with the new keyword new technology. Right, your input is solar, commodity is your solar radiation, unit gigawatt hour. Then comes the commodity for output electricity and in unit gigawatt hour. Again, AFX basically what is doing, whatever the potential, you're fully using it. One, that means you are forcing the output from the whatever potential you are getting. If you want like 30% of it that is used, 20% of that is used, you can do that also. Again, weather factor is your whatever the weather classes we have mentioned above. Then comes again the cost, fixed cost, investment cost. Again, you mentioned the installed capacity of solar. You can also degrade the generation also till whatever year you want according to your specification. Again, if you want to install new capacity for solar, so you want a new capacity, so you will start the investment from 2020, right? From 2020 to whatever year you want the investment, you will mention here through the keyword start and end. Again comes the operational life of the plant or the technology. Then what we are doing, we are putting a constraint on that. It's a geospatial solar installation limit. So what we are doing, we are just using only 2% of the territory. So if you want to add solar installation in Karnataka, so it will use only 2%. It will not exceed more than that. Then again, whatever specification you want 4%, 5%, you can enter to this constraint. So in geospatial there will be some constructed area, those you have to remove, and how much area left to construct your solar plant, you can, then how much percentage that you want to use, you can put it here as a constraint. Then comes the wind. Again, we'll entering the input, output, their commodities, like for wind, input is wind, unit is gigawatt hour, output electricity, unit gigawatt hour. Again, you are forcing the output, you are fully utilizing the potential with AFX fix. So if you want to put a upper limit and lower limit of the generation also, like 10 gigawatt hour is the generation, and if you want to put limit upper and lower limit, you can put that also on that. Then comes again again you are plugging in the O&M cost, investment cost of a particular technology, then again stock installed, install capacity of current year, and then we'll enter the start and end. Again, this start and end reflects whatever year you want to start the investment. Again, if you, there is an option, if you want a particular, later we'll discuss, Arun will discuss, if you don't want any capacity installed in whichever year, we can do that in the later year, and or you can hash the investment years. Again, here also what we are doing, we have constraint on the wind installing plant. We are using only 10% of that region. So if Karnataka, we are using only 10% of the Karnataka region for wind installation. So beyond that, it will not be installing any new plants or new sources for wind.
I have a question. So how do you distribute that 10% area?
We have assumed it, but if you like, what you can do is like whatever the area which is wasteland, or you can calculate that area and how much percentage of you can use that through that. But that you have to separately calculate that.
So this program will identify which one
This
is
program will, you can only input your how much percentage of data you want to use. But if like, you can also add few chunks also. If you like, you have a constructed area, you have some cities, you can overlap those over GIS mapping and remove those constructed area from the land, and whatever the land is left, you can then use it. And whatever the land area you can calculate through above land area kilometers square, and through that you can install any source you want.
That feature is currently not
It's not there right now.
Thanks.
Okay, you again you can enter any new technology with these parameters only. Whatever the parameters you know, you can enter through. Like here is like whatever the investment cost, fixed cost for green hydrogen is, you can enter again this investment cost you want or not. Okay, we'll stop here. We'll have a lunch break for 1 hour. Any questions?
Well, I have few, but
Okay.
maybe we can break for lunch.
Okay. We'll meet at 2. Thank you, everyone.
Model Bengal or something. How much time it will take just to model one system? I mean, for example, for the take of Karnataka, how much time it will take to model just Karnataka system itself?
request all of you to settle down so that we can begin the second part of the workshop. Thank you.
Again, good afternoon, everyone. So most of the questions were related to flexibilities of the model. So if your data sets are into 15 minutes time resolution, then you have to put a weather data also of 15-minute time resolution. Nothing else where you have to change the slides, because it's the taking time as it is. Okay, so then the demand data is also should be of 15 minutes, right? And if you want to enter any new technology, as one suggested, a title and all, so you calculate hourly for every hour. You calculate the power generation from tidal, and then you plug it into the model. Rest is taken care here. You don't have to enter anything besides the technical operational parameters. Like if you want to constrain that technology, output, input, anywhere. That's how in that class only new technology you can constrain the slice wise, as in if the slice is for 1 hour or if it's for 15 minutes, you can constrain that, or you can constrain annually. So you can constrain the annual generation for the whole year.
Any number of new technologies can be added, or just
Yes, any new technology can be added.
numbers?
Any number also.
Type and number.
But then
Suppose the technology is coming in like 2030, 2025, something like that, then when it can be added?
Technology is coming 2030 as in? Acha, futuristic. Yeah, then you have to put a respective year according to the technology. Okay. So if it has not come yet, but you want to enter for some new technology in 2035, then you put the model year 2035. Then it will take that model year and put that technology in 2035. If you are calculating for future years. Shall we start? Yeah, okay. So next comes the commodities. Commodities as in you're defining the input and output of a technology. So the commodity could be like electricity, that is the output of a technology. Output could be heat or gas also. Here we have not entered, but if you want the heat and gas to be there, you can put heat, then new commodity, and you tell the slice if it's hour wise or annual. Same goes for the heat also, gas also, right? And CO2 also here. So solar, wind, onshore, offshore, high voltage. And you can also enter the carbon, any carbon based technology. You can enter the carbon emission factor. So for coal we have entered like for like different types of coal is used, so there is different carbon emission factor. So you can use that, enter here. For dummy purpose we have used 250, but for any carbon emission factor you can put here for coal, for whatever type of coal you are using. Then you enter the gas, same with the keyword new commodity. You enter the name, description, slice you are defining for either hourly or annually here. Then again NUC stand for nuclear, you can enter here the commodity, right? So we have entered the carbon emission factor for coal, right? This is to calculate how much CO2 emission was there if we involve thermal throughout the year. Then comes the demand. Here we have demand, like as I showed you earlier, it's from 2010 to 2019. So here we'll be filtering the data, since we are validating for only 2019. We'll be using only 2019 data for demand. Again, the demand is converted into an object with a class name new demand. So here you will be entering the demand as in you'll be using the commodity in demand is electricity unit. Then you'll be entering that demand in that DM data frame. So whatever state you enter, there like here is Karnataka. If you want, if the data frame contains a Tamil Nadu also, you'll do it a vector formation like C and bracket K and then comma Tamil Nadu, and you can enter that. Since the data frame contains both Karnataka and Tamil Nadu data. Again, we are for consistency, we are maintaining 2 gigawatt hour for electricity. Then again, this is a chunk from demand milestone years. So if you want to execute for 2050 at an interval of 5 years, like from 2022, 2025, 2025 to 2030, this chunk is you can use it for milestone years. Currently we have hashed it, since here we'll be first discussing the validation for 2019 only. Then comes the supplies. Supply here means, so we are putting the resource into action. We are supplying that resource to the technology. This is what it means. So for solar is like solar radiation. You're transporting your solar radiation into power, usable power. Same goes for wind. You enter the unit, slice, commodity. Same for any other technology, you'll be using the same parameters. And like for hydro, or if you want to limit the resource also, if you want to use like you have a coal potential of some 100 ton, right? So if you want to use less than that, you can fix that also through dot fix variable. Again, we have shown here the supply gas, supply oil type also, biomass. So any commodity, so any resource you are supplying to the technology, you can enter it here. And here you can enter the fuel cost also for coal, which this has been taken from CRC tariff report. Then we are here using 2 type of energy storage, hydro reservoir storage and battery. So for hydro reservoir, we are using reservoir data. So as I told you, we have limited the capacity of a reservoir to the maximum equivalent energy it holds throughout the year, right? So and we have converted that data frame slice wise of reservoir data to class new storage. Again, this is a keyword. This will be called from energy RT only. Again, you made the reservoir as a new storage, and then you'll be entering all those parameters. If there is a charging efficiency of that, charging efficiency as in how much water is going inside the reservoir, percentage of water, and you want to have that efficiency also, that is there. Again, the stock basically is a capacity which has been fixed for reservoir. And if you want to attach any investment cost to reservoir, like if you want to increase the capacity of the reservoir, then you add this through start and end of investment year. Then we have given some constraint. For example, if you don't want to put the parameters, you can put the efficiencies or even any other efficiency in the form of constraint also. So if there is no loss between output of the reservoir till the input of the turbine, you can do it like supply out from the variable supply out to the technology or storage input. You don't want any loss, so you can show it here. Same goes for here also, from dam to turbine head. So storage out and input to the technology will have is 0. This is how also you can put the parameter. As in, if you want some efficiency, you can put here like there are losses, some amount of losses you can put here also. If here we have kept 0, but you can put the losses here also. So there are two ways of putting efficiency. Either you put it through the class objective, or you put it through constraint. We'll execute this.
Will there be any check being done in case by chance I put it in the class and it also I'm putting, then it will check?
So class is only for declaration and definition. Here it's your object. So in object only you are defining the data frame. Class is just you're declaring the name of that and defining it. Next comes the batteries. So for batteries, you put the operational life. We want to put the investment here is like base year only. We kept the investment cost, and you can put slice wise or slice wise charging efficiency, input discharging efficiency, to storage efficiency in this chunk. Same principle is being followed. You use the keyword new storage and you create an object of battery storage. And these parameters definition is already defined in the class in energy RT. So you just have to enter the values. That's it. And if you want to see what else being defined in this class, you come here and you whatever you have named the class like storage battery, you click here and you can see the different parameters also here. Like, let me show you. See, so all these definition has been entered here. Like aux is like auxiliary commodity. Like with coal you are putting oil also, or you are getting from output you are getting heat and gas also. You can put auxiliary commodities also here. Same goes for every class mentioned here. For technologies also, for storage also. Constraint it as a import only. So what we have done. This new import is what we have done. This is called a class. You call a class. If you want to do a constraint also, you can do it. But in constraint you have to put a price. How would you do that? Cost. So what I mentioned, you can do it in class or you can do it as a constraint. That is for energy units, right? Yeah. No, not curtail your supply, curtail your demand, because your supply is not enough to meet the demand. Yeah. So we have, that's why that's Abhishek mentioned, okay, we have use a dummy cost, penalize demand curtailment. Why? Because every time then it will choose demand curtailment only. We don't want the model to choose a demand curtailment.
Just one advice, rather to say that it's penalized, you should use this word that it is procured from expensive resources.
Okay. Suggestion duly taken. Okay, then you can import and export class, right? So what we are here doing is we are not modeling any import and export here. We are actually using the import and export of an actual data. But if you want to model it or you want to restrict it, you can simply fix your import, whatever amount you want to fix, or you can upper limit or lower limit through command like this. Okay, so but for this case, for validating the case, we have kept import and export the actual data, hourly actual data. Okay, now I would like to hand over to Varun. He's also an energy modeler, and he's been the core team member of this energy transition group, Sustra Lab.
Let's bring the elephant in the room, that is the model, how we are doing to do that. So in this one, first we will call off all the repositories which we has been made, that is electricity, solar, wind, hydro, CO2 and coal, and also on the biomass. So these are the basically the other factors and all the things which we have called for over here. Now, once we have called for, we just need to know that how many variables have called for. What all the things are there. So right now we have 20 variables which we have called. Basically, these are the inputs which has been given, and what are the names of that one, which has been given on the console over here. Basically, electricity, solar, wind, hydro, coal, and CO2. All these are the basic variables which we have called. Now we introduce a model class object. That model class object which we have given over here is the model one. That is the new model which has been taken. In this one, basically, I have been given the discount rate of 8%. This is basically with respect to the SBI rate of interest which has been given. And from that one, where we have developed now modeling appropriate repositories and other things. Now, as right now, I have done all these things. Now, I want to see that are there any duplications which has happened? Sometimes the problem is like we might have taken solar, and during the coding of like so many lines, sometimes we miss it out. Like I will be repeating the same I'll be calling the same variables again and again. So that will be double adding. So to avoid it, I will just making a check over here. That is like, is there any duplication? So if I say that one, and I will see that there are no checks. So that means that I have done a correct coding over here. There is no point of like. So now next let's check into the time slices, because like time slices are very much important, because so yearly, hourly, annual generation of the data have been given and the things. Now the beautiful part over here in this model, I would rather say like, now as Samrit already told about the demand, what if the demand rises by 2040? Because like today the demand, let's assume, is to be 100 units, but tomorrow it might not be 100 units because the population is increasing and everything. So how to do it? What is the growth rate which we need to be considered? CEA will be giving some growth rates, and some other people will be giving some other growth rates, which is a better one to take. So how to, but computer is a wonderful thing. I can tell, if Samrit is my friend, I can say that do take the demand like this, but computer understands ones and zeros. So that one, how we have to do it. So for that one, we have considered the few milestone modeling gears. That is what we have considered over here. So you can see it like right now, start end is 2019, which has been in this model. Now I will just little bit tweak over here. Like I will be saying the milestone years in the 2060, how it will be. So I will just run this line. So now let me see like how the shape and everything will be coming up over here. See, the magic over here comes over this like this. See, I have taken the repetition of 1 year, the differences of 5 years, 6 years, 7 years, which has been shown over here in this thing. So I won't do it right now to show like all the modeling how it has happened because of the time duration, and I know that lot of people have a lot of questions, so I will just click this one off and move on to the final output parameters. So for example, now I will be giving the model description. It is a Karnataka power system with the 1 region, 1 hour resolution model, and 3 types of renewable energy sources and 2 types of storage. Now we will have with the little bit of like this has been done. Now we will go with respect to the solving options which we have taken. Why we have considered CBC our solver option. To be honest, CBC is one of the open source available solver. That is the reason that we have taken. The other most available and the easiest option on the solver is Cplex. It takes a lesser time, but it is a paid one. And the next one is right now the world is going with Gurobi. That is also there, but as we work on the stipend of 35,000, we don't have the money to buy the 20 lakh rupees of solver. So that's the reason that we go with CBC right now over here. So So now let us run into the scenarios. That's the reason that justification behind that why we have used that solver CBC. So now the new constraining option which we are considered is capacity in this one, where we have you can see it over here for the each data frame, and we have bring down like the what is the new capacity addition which is going to happen and all the things. Now let me do the model adding of each and every variable which has been given over here, like the storage hydro, storage batteries, reservoirs, import export, and etc., and also the demand. Now I will interpolate the results on the one parameter. So this is a Karnataka 1Y scenario. Basically what this scenario is all about. This is a scenario where we will be, right now we have the actual electricity generation happening in Karnataka. Now if we optimize it with respect to our model based on the weather data of the solar and wind energy, solar irradiation and the wind speed, how much of energy generation can happen and how much is the validation? Are we able to get the least cost option? So that is how the Karnataka 1Y scenario has been developed. So for that one, let me check like are there any options with respect to the actual and the modeled one. So here it is take the interpolations of the model, and now I will write the modeling code with respect to the data in the folder which will be solved over here, and the solving will happen with respect to the GAMS. See, it's a simple option. Simply it has been done. To be honest, it is 8760 data points, so that's the reason that it is going so fast. But if we increase the like for the another 10 years or 20 years, it will take some time. So that's the reason that I'm not showing you guys the milestone here, because like it will take half a day for me to run one set of coding on each scenarios. So this is one of the scenarios which I will be showing the results in the upcoming thing, and the next another one is the only renewable energy scenario. So now let us see, like we will say that we will just go with the Karnataka renewable energy scenario by avoiding the thermal power plants. How much of generation can happen? Are there any if there are any shortages, how much of the new installation capacity need to be added, and what will be the capacity utilization factor that is being carried out over here. So this is the one which has been like this is how the modeling can be happen. So again the same process of like the CBC solver through where we are using GDX RRW from the R to GAMS, which has been interpreted over here, and we will get the results accordingly. And I will run the scenario, renewable energy scenario, and also on the, and I will solve the model. So now let us see like the what are the results of it, of all the both of the scenarios. See, you can see that for the Karnataka optimal thing, we have got 1419.608 billion rupees, and also with respect to the Karnataka renewable energy scenario, the optimal is 1530. Here, why in the renewable energy it is increased? Because of like the capacity addition which has happened with respect, because we have removed the thermal power plant and we have added the renewable energy sources. How much of the things is being happening, much of capacity added. But right now, for the betterment of the next processing, we will just go with the Karnataka renewable energy scenario. Like I will just show you guys how much of capacity has been added, not only everyone. So see, you can see over here, I have selected the scenario. Okay, and you can add n number of scenarios according to the user specific and user variability. So now this is the beautiful part over here. You can see over here, we take new capacity. See, we know that there is a, if I take the renewable and a thermal power plant, which is almost contributing to the, almost contribute 30% of the total electricity generation. Where will be the new capacity of solar and wind will be increasing? So you can see over here. Now, to make the Karnataka in 2019 to completely match the supply and demand at every time frame, we have to have an extra capacity of the solar of 1.51 gigawatt and 8 gigawatt. See, this is how we will be able to see that, okay, a new capacity has been added and this much of capacity is required to make sure that at each and every time frame, supply and demand has been maintained. And we are seeing like, okay, this is the, this is 4.67 is the hydro capacity, which has been kept constant for the every point, and also for the 2040 also we are kept constant, because like we have a policy right now that you can't have a hydro power plants in future. And also on the solar power plants, that was 6.7, and we have added 1.51 over here, 6.07 to 1.5, so total capacity come around 7.6. And wind is 4.78 right now in 2019, which where we have adding another 8 gigawatt, so that the completion of total generation with respect to demand matching will happen. Now I will move forward with the and this is a generation point of view, how much generation is happening. So this is a thing which we have considered, like how much of capacity has been added and all the time slices and all of these parts, which I won't take much time of it, so that I will just show you the result of like how it will be incorporated. These are the only inputs which you need to give me over here. This is over here, the graph which you are seeing is the total of storage input and storage output. Because if we are using solar power plant or the wind, it is intermittent in nature. It is better to store whenever there is a maximum generation is there, and whenever the minimum generation is there, you can give it to the, take it back. That is why it is been shown like this. Okay, now we have this emission also. We can find out that in the renewable energy scenario, you can't have any emissions. Basically, there will be emission either through the export and import lines. That's it. That's in the part. But you know, if you are using thermal power plant, how much of emission is happening, that can be considered over here. Now, our new levelized cost of energy has been also been calculated. How much is the least cost value of the thing, and we have taken the supply cost, installment capacity, initial capacity cost, storage cost, trading cost, O&M cost, and the storage of O&M cost. All these costs has been considered over here. If you have any other cost also, you can add it over here. That is also not at all a problem. Now we can see like the total cost which has been given over here, with because like the new capacity addition have happened with respect to the solar and wind, how much of the new capacity and what is the O&M cost also, which has been shown over here. So this value will be given. And the best part of this model is like you can export all these values to the Excel, which is easier for you guys to, if you have to analyze it and make it into a better part. So that means that it is a easily user-friendly tool. That is how it has been developed. Same thing it is done, which I have done. And now I have converted into the time slices to date and time, and what is the ranges of like, basically, this is a point where we have shown of like, we have taken the value of 8760 in a calendar year from January 1st, 12 o'clock to the December 31st, 11 o'clock. That is 8760 data points. And adding all the things and now combining the cost, and finally I will show you the value. This is where it has been done, and now here comes the levelized cost. Okay, this is how the levelized cost looks like. I know why it is not I am unable to zoom it out. So this is how it is, and now right now let us look into the real actual value, which is right now in 2019 Karnataka, how it was. So we can see over here the storage input, biomass, export, import, wind, hydro and thermal were the basically the sources which has been there. As Samrit have already spoken to you guys about like the real data, which how the Karnataka actual system looked like. And now we have converted some values, and now the fuel fact mix. See, you can see the actual data, how it is, how the shape has that, how the shape of for a few days. Yeah, please go ahead.
Some negative values, and we say that to be export.
Yes.
What is the inference?
Export means, I didn't get your question, sir.
We have negative.
That is being sent to other states.
Extra. Or we have some treaties with respect to the other states. Sometimes, like for example, I will tell you, Raichur Thermal Power Station we have like 80% of the generation comes to the Karnataka and 20% goes to the Maharashtra. That means that 20% of like, though the plant is in Karnataka, we have to send 20% of that generation. What have happened to that one? Those are the points which we call it as exports.
Do you consider the imports that has been taken from national?
Absolutely. You can see it over here. You can see the line over here in this one. Imports is also there. This is the one, imports. Export and imports are there. Now we will work on right now the modeled one. So in the modeled one, we have taken all the scenarios and all the storage input, and what is especially all the generating technologies which has been considered over this one. And right now we will be looking at like what is the final value which we are going to get. So is there any names and all the things? So this is how it is done, and right now you can see like the demand is there, hydro is there, solar is there, wind is there, storage input, storage output, and export import, and EIMP is basically the connected load, that is the unserved load which is been given. That is a low generation load. See, this is how the model operation looks like for some of the days. And we can say this one the Excel format and whatever, wherever you want to, according to a folder, and then you can see it. Now let us compare the actual versus the real data. This is a nice thing to do because like we know that how the shapes have been given. So let me show you the final result output of this one. Oh, this will go like long and long. So I will just stop it over here so that I can take the PPTs for you guys in the next one how we have been done. So this is the real output and this is the real output which I will show you right now in a better picturization in the upcoming slide. So this is all about the coding. Now we will go into some of the aspects of now we are done with the this is the basic code where we have to do. Now how the results have been interpreted and all the things I will just show you right now with the PPT. Okay, now we have seen that how the model actual system and the model system has been developed in the thing. Now, right now the beautiful part about the K1Y scenario which I spoke about, that is the model system. Like, are we able to decrease the cost of the current optimization sector on the generation sources? We can do it because the model has shown that 148.3 billion rupees is the total cost of the system compared to the 154 currently which is being right now taken in the Karnataka electricity system. And you can see over here all the demand is being met currently with respect to the thing, and in the model we have little bit of storage also, that is 0.04 terawatt hour, 0.04 terawatt hour of storage is also been there. And now the best part about the renewable energy share is in state is in the model electricity system, what we have considered over here is the giving the preferences to the renewable energy sources. That is how we have the excess of 64.17 of in-state renewable energy generation which has happened. And now the beautiful part of we can see over here actual system how the peak and the variation has happened over here. See, you can see from the hydro power plant in the actual system the peak, minimum load of was 34, but right now it is 214 megawatt. That is how the shape has been changed right now. That is the minimum, and the average has also been same though. But here the differences between the peak and the minimum has reduced. This is how the model and the actual electricity system has changed. And also with respect to the CUF, also we can see in the model electricity system, the CUF of wind has increased to 26.33 from 19.93. That means that the higher utilization of the plants have been considered over here.
Now, with respect to the validation of the model, you can see over here is like the actual system, there is a little bit of like mismatches happening, but in a model electricity system, there are no mismatches. And also with respect to, there is an increase in the renewable energy generation, and there is a smoother curve of the renewable energy generation, which has been considered across all the 4 seasons, which we have shown it over in this one. Now, after all this thing, now let us go into the scenarios development. What we have done is like we have considered the 12 scenarios, that is 3 on the demand side, 4 on the supply side. 3 demand side scenarios which we have considered over here is like one is a baseline scenario, and one is optimistic, and the one is a pessimistic. That showcases that from 2019 to 2040 in a baseline scenario, we have 4.52% of compound annual growth rate of increase of demand from 2019 to 2040. These 3 scenarios which has been taken from the CEA report of long-term electricity demand forecasting. We didn't do it from ourselves. This is a demand which has been given. Now on the supply side, we wanted to see that how the variations happen across the sectors. Like only with respect to renewables if it's there, only with respect to trade it is there, and if we take only the coal power plant, basically we wanted to see that the complete spectrum of the thing. So what we did is like for the base case, for 2019 only we try to validate the scenario. Like with respect to, we have considered all the electricity supply source, and we have validated this scenario. And now we have taken the Karnataka renewable energy trade. These 3 are the futuristic scenarios which we have considered over here. The futuristic scenarios which we have considered in the K renewable energy trade means the problem is we have in the renewable energy trade, we have considered only the renewable energy sources like solar, wind, and import and export, but we have excluded the thermal power plants. But in the renewable energy no trade means we have considered only the solar, wind, and biomass. There is no trade and no coal also, thermal power plants. And in the renewable energy K RANCO is like we have considered only the coal, and export import has been excluded in this one. So these are the nice names which we have given, I know that. And now we will go into the comparative analysis of all the scenario. I would like to say that there is one beautiful thing you can see over here. One of the interesting fact which can be seen over here is in the renewable energy trade scenario. If we are having the same thing, and if we exclude the coal thermal generation, we will be having a shortage of 19.66 terawatt hour of energy units. And with respect to not trade, only with respect to like coal, we are including only the solar, wind, biomass, and hydropower plant. We have like just 35.39 terawatt hour of wastage of no non-serve units. So how to do it? What is the next to overcome this? How do we can go ahead? What is the things which we need to do? So the best part about like is we will be doing on some of the results and discussions. So you can see over here, interesting is like this is the Karnataka current in 2019, the electricity capacity, installed capacity over here. Now we can see over here, this is the 148 which I spoke about, like 148.32 billion dollars of rupees is there, no? So how the generation has happened and how the capacity utilization has little bit increased with respect to in the K base here. This is how we have shown it. Now next go into the next K renewable energy trade. Now we have like 19.67 of terawatt hours units of electricity, non-supply of electricity. So to overcome this 19.67, we have to have an additional installed capacity of 7,470 megawatt of, basically 7.4 gigawatt of wind power, and also on the 2.3 gigawatt of solar power which need to be added over here. And now we can see that the capex has been added of like because like of the wind has been newly added. So how much of the variation has been given over there. So this is how to overcome that. This is the costing which has been came across. Now with respect to renewable energy non-trade scenario. So now we have like 35.39 terawatt units of non-trade non-generating units. So how to come there? For that one we have to have the excess install of 13.7 gigawatt and 3.7 gigawatt of solar. And you can see the costing over here and the CUFs and all of the things which has been given. These are the things which we have got it from the model. So this is a beautiful part of like our IDEEA model, which gives us the complete thing.
Yeah, so this installation is concentrated or can be distributed? I mean, the model can give that answer as well?
Yeah, it can be distributed across the state.
Across the state.
Across the state.
So
and we have considered basically we have considered few of the areas with respect to, like, if it's a green area like the Western Ghats of the Karnataka, there you can't have any of the solar or wind installation. Those aspects has also been taken, where there is a higher solar irradiations on those plants.
So the model can handle that part.
Yeah.
For that you need to feed in different costs as well, area wise, right?
For one state we are not adding different area wise, right? For the state to state we have adding the cost.
No, putting solar generation at one location, Bengaluru, and putting at some other location in Karnataka, that might cost different.
Yeah, that is there. You can add on those points.
Okay. But that feature can
that
be
feature is there.
in
Yeah, absolutely there. I think Samrit have shown that feature, right? Yeah, you can enter it. We have shown that we take cost
but
and all
just
that.
again reconnecting it with the data set that we are working with MERA 2, the block restriction will be still there, right? I mean, we cannot model at the further level than this.
What you do, whatever area you're putting, put through the region. You put the region, then like there are 2-3 regions you have selected. So that region you select, and according to that you put the area cost corresponding to that area, and then it will take that cost.
But that is not considered for this story.
No, this no.
The cost part, what you are going to consider? What is the cost part you are taking? Like installation cost or what are the other costs?
Yeah.
We are giving the economic costs. Since
cost.
we come from a society angle, economic cost means investment cost, warranty cost, and fuel cost.
What about real estate?
That comes in investment. You have to set up a, say, solar plant or a thermal plant. Part of the capital cost.
See, if I have to set up a next place, I have to procure that also. And then I have to look at
That's a part of your capital cost. That's what I meant by investment cost. It's not just the land, plant, and everything.
you have a demarcation which clearly says what is the capex, what is the opex?
Yeah, we have. Here we have given it, right?
Oh, okay.
Capex and opex completely. The total cost is a summation of capex and opex. Oh, sorry.
So this result would make sense with the location. Why I'm telling that, because we are already working with the data set MERA 2, and it has different. It has shown that different capacity, different zone has different capacity of the generation. When you're saying that 13.7 gigawatts of installation is required, we need to specify that what location. If we install that, then we will get the required energy that will ensure that no curtailment of load will happen on so and so. I think that is missing part in this story. Makes sense what I'm trying to say?
Yeah, it makes sense.
Okay.
We'll definitely try to incorporate those things.
Thanks.
So right now, like, this is the first exercise what we have done with the model. So we have focused on macro level things.
All right.
On that.
Thanks.
Thank you for the suggestion.
And sorry, is there any way you can put a limiter on the budget so that it can show that okay, in 2019 you may not be able to expand as much, but it will take you more time depending upon the budget, and how if you allocate the budget properly you could get the maximum output?
You can add that as a concept.
Okay.
And just for more clarification, when you compare results with actual, those actual are actual data, right?
Actual data.
And that system must have considered all load flow constraints as well as system dynamics and everything, which we are not considering. Imports, exports, whatever data you have showcased.
Okay.
Those numbers must have come after considering dynamics and stable and everything, and whatever we are comparing that with, the model never considered that.
No, model has considered the import export on the same value.
No, import export is okay, but at the same time, are we ensuring the stability of the system, or how at the micro level, how power flow would have operated in that particular region if we are putting this much generation at that and that? So what I'm trying to say is, the comparison doesn't make sense, because one is actual system, which I have considered much more detailed version.
Yeah, please.
And the model, what I'm trying to understand is what kind of detail level we have considered as far as model is concerned, so that we can compare those results with actual.
No, so the comparison here is same again. You could get the impression that the comparison is mostly for sense checking. So of course, load flow analysis, AC load flow, DC load flow, and how you model AC lines, high voltage lines. A lot of dynamics there. But then that's more of a say operational kind of work, and even there's a lot of constraints on how much system visibility you have. So here again, there's a very complex network of, say, as you mentioned, right? So it's a very complex network of entitlements in central power stations. So here the intent, I think, is mostly to sense check.
Okay.
And it's not totally something very implausible is not happening. That's rather the concern. And then it's sort of say, maybe is there a way to restructure the PPAs, the historic PPAs, when they expire, maybe to get a better, more optimal portfolio. So that's in that sense the comparison.
It was not communicated that it was a sense check.
Yeah.
I was taking it in literal sense that it is it is not one-to-one comparison.
It's not. It cannot be because again the system operates. There's a lot of complexity there.
Right.
So AC load flow is non-linear. Even if you create a model, you still cannot replicate what's actually happening in the system.
Understood.
Even with that, yeah.
I was just wanted to clarify that what levels of details we have considered in this model.
Yeah. And the other part that you mentioned earlier. So say there's a grid, spatial grid. You can always downscale if you want more specificity in terms of generation asset. So you can downscale. So say you can break it down into maybe 20 smaller blocks.
Okay.
So assume same resource availability, but then the land availability constraints could be different for each block.
So
and then
that's a different problem altogether to handle.
Yeah. And then transmission, or you want to assume a pool or something. So that has to be for transmission. Yeah.
Of course, we cannot mimic the actual system, but I was just trying to understand that what levels of modeling we are considering for our group. That's it.
Yeah.
Thanks.
By actuals, we actually don't go in, even for actuals, we don't go into the load flow study part of it.
No. So what numbers we have got, I think what you projected,
That is
that came from which?
The actual, if you can show the graph that date-wise we had. So I'll just clarify on the data once.
Yeah, here.
So it is basically the source-wise generation. It's not even plant-wise. Like how much was the total thermal generation on that day? Or for every hour of that day, how much was the hydro generation on that day? That is what the actual data is, and we are comparing with our model result, how much it should have been.
The generation dispatched must have considered all detailed level of modeling. That's what I'm trying to understand, which we are not considering in our model.
No, it doesn't have modeling. It's like what had happened.
What had happened, that must have considered the detailed level of system. That's what I'm considering. Like, for example, you need commitment, or for example, dispatch.
Yes.
For dispatching your generation, let's say some hydro has been dispatched to some value. That decision must have come with a consideration of detailed level. And here what you are considering, that is not modeling at that level. That's what I'm saying.
Yeah, so I think for actual system operation, they're not using modeling as such. So there we have a system of, say, self-scheduling. So the system operator will have a stack. They'll have something for which they don't need to reveal the marginal price, and then they will some entitlements from the central or whatever private portfolio they make. So they don't use models for dispatch. For procurement optimization, if they're doing, say, a year-long or, say, 2-year-long exercise, deciding whether to go to market, do a new PPA, make own investment, they'll do a modeling exercise. For the day-to-day operation, with which the comparison is of, they don't do the modeling exercise. So on a daily basis, they'll see what is the availability. Some plant will probably a day before declare availability or not, and maybe some maintenance or what not. Basis that, then they dispatch whatever they have.
That's the practice we are talking about Karnataka.
Everywhere. Say in India, everywhere, that's how, say, the state load dispatch centers operate. And so.
Thanks for that.
Yeah.
Thanks for that.
Modeling that you have done here, actual and model. So can I use this for identifying what should be dispatched from each power plant? Is it possible for me to identify?
Yes.
Yes.
Yeah. In our study, we have considered it at an aggregate level.
Every hour you are told, so it shows that, okay, then if I can predict for 1400 hours, and 800 hours, 8 hours, so that means I can just schedule my generation at different points and...
It does exactly that, along with the capacity additions. So if you do just the dispatch, it's called production operation simulation or dispatch optimization in some sense. If you assume capacity to be fixed, as in the base year. If you're doing, in addition, the capacity decisions along with it, that is when we call it capacity expansion. And the problem is with the dynamics introduced by renewables, you need to do both simultaneously.
But how we are going to allocate the generations?
So first rule of thumb is, if you're operating hour to hour, you'll do a merit order. So deploy cheapest first. But then comes the additional dynamics of ramping and whatnot. There are constraints how much you can flex your generators from hour to hour. So you need to honor that. And then the rule one is a merit order. So cheapest first, and then stack them up at each hour. But then from 1 hour to next hour, you have additional constraints of dispatch, resource availability, solar is available, shining or not, wind is available, what is the status of hydro, that
For
along
example,
with,
if I take a scenario, now suddenly there's a demand in Bangalore, and then I want to procure the power from X place. How am I going to decide which X place should I procure?
cheapest first. So you have the cost information, you have
Out
the
of
transmission.
the available ones, cheapest first.
Cheapest first, yes.
Just how do you, specifically in India, if I take Europe, this model is excellent because I can price my, based on demand, I can do a dynamic pricing.
Okay, yeah, let you
Yeah,
finish.
on a price perspective, imagine if the board has to give like demand, like as per this demand, it has to give the supply.
Yeah.
And you said you go the cheapest first. Now the demand is higher, which means that my cost of production is going up every time, right? But when it reaches the customer's value is fixed, right? Which means that maybe like the capacity I have right now is not helping me like give the power at the right price to make right profits.
Consumer's price is not fixed. Consumer's price is not fixed. They pay actuals.
No, if I am the user, how does it?
If I am a consumer,
Yes.
Like whatever electricity bill I pay, that
Yes.
is based on actual power purchase cost.
No, but for me it's unit price fixed, right?
It's reconciled. There's a phenomenon called two-in-one. So it's based on the assumption they'll do such an exercise that
Okay.
next 6 months regulator will approve this is the price. If there's a too much discrepancy, say
Okay.
demand is higher than what you had anticipated, so you incurred more costs than you had anticipated, then you file a petition to the regulator. Then I'm not able to, then it will adjust accordingly. That's how it
So
operates.
that adjustment will done on your next year's tariff rate.
Got it.
Yeah, so that's how it operates. Yeah.
Just a follow-up question. So you said that merit order is possible, right? So based on cost means for coal power plant, it will be variable cost based merit order expense. So you are only considering variable cost.
No, so merit order, again, if it's, so there are two things here. One is the operational aspects. There's a legacy system operating. The transaction mechanisms, the real system, that's a separate thing. That's complex. So in that case, the contract happens that way. So fixed cost is paid upfront. Then variable cost you have to pay as and when you schedule. And you have the right to use or not. That's the PPA. Here it's including both the costs together. So we are making comparisons between, so in here, we are planning from a perspective that I control the investment as well as the deployment cost. But the real system, because it's already there in place. How the system evolves, the PPAs are already in place.
Understood. So do we have suppose we are only considering what discount demand they have to meet. If you are designing a system only for based on discount demand, because when you consider overall demand, there is open access and whatnot, and then discount sets. If I am only designing it for discount, and then if I am applying merit order dispatch, will this model give me the flexibility to give the merit order based on variable cost alone?
No. So currently, you can run the model in that format if you want. That's simple. Then there's not much dynamic happening. Other than ramping, there's no other dynamic to account for. But in this case, we're accounting for the fixed cost as well. In this when you're running it in the capacity expansion model, you're accounting for both the costs. So if you want to run the merit order only, it's simply so you take 1 hour at a time, and then the ramping is another dynamic which is being captured by the model. And it's as simple as so at each hour you see what all is available, then cheapest first and make the stack. So otherwise it's simply that. If you do ramping, then basis wherever you have sharp gradients in demand or the renewable resources, that is where you'll get some more dynamic. So it will be slightly different from the simple merit order.
So just to add on a few points, the cost considerations which the discoms do and what we are doing is different. We are not considering all the transactions cost. We are considering only the economic cost or the cost to the society. So we don't have, for example, depreciation. We don't have interest on loan. So those are like developers' cost. We are considering only the cost to the society. So that's why it will, look little different from your actual, the P&L statements.
Just a couple of points. Correct me if I'm wrong. See, I think there are two things. Okay, one, what is being presented. The other is what is possible to be modeled. I think there is some kind of confusion. Okay?
What type of confusion?
For example, what is presented, overall the audience I'm telling. So what is presented is what you have done as a case study. Okay? The model capability will be high, right? We can tweak it according to the needs, I guess, right? But so what is presented is just as a case. So if we want merit order to be chosen, we can choose that. If we want something else to be chosen, we can also choose that. Right? Model all of that.
Merit order is something like you have to consider the first renewable energy sources completely combustion, and then based on the what is the another available the cheapest source of energy that has been given, right? That is completely been taken.
Yeah, so, but the model has the flexibility, right? Based on what we want to model, I think it gives the flexibility.
Yes, model has the flexibility.
Yeah, I think that point has to go clear.
Oh, thank you, Mitraj.
Do we have a model? Will it predict when we'll get the ROI? Any sense?
No.
Again, as I said, we are considering only the cost to society,
Got it.
not the business perspective.
Got it.
The results which we have shown right now is just on the economic cost, not on the business cost. So I think so we had the major discussions on this point. So now let us go into some of the futuristic scenario results which we have considered over here. So we have considered on the three pathways of these results. One is on the operational pathway, other one is on the environmental pathway, and other one is on the economic pathway. In the operational pathway, basically we have considered in the 2025, 2030, 2035 and 2040 what will be the generation mix of each of the electricity generating sources, basically how much of thermal generation can happen, hydro and other things, based on the three supply side scenarios based with respect to the three demand side scenarios. That is like total of 9 scenarios which has been considered. How will be the shaping of, like on the economic, we have considered the total system cost, total unit cost and the capital and the variable cost, and how much of CO2 emission can be avoided. That is how we have considered. First, let us go on the baseline scenario for the KA renewable energy trade. That is my excluding thermal, we have considered all the energy generating sources. So this much of the capacity addition might happen, will be happening with respect to the this is the generation wise of like all the solar for the 2025 to 2040, how much of generation can happen, and for that one how much of capacity is required. This has been shown over here for KR renewable energy trade and renewable energy scenario, and this is totally the unit cost which will be increasing for the how much of for the KR renewable energy trade and and the unit operation cost of all the scenarios for the baseline. Now we will go into the next of optimistic scenarios. For the optimistic scenarios, what we have considered over here, same thing of this is 4.86 compound annual growth rate of demand from 2019 to 2040. So this is the generation required and renewable energy trade, basically export import. We have made an assumption in this model that for all that renewable energy trade, that is like the export import values which has been considered, it is same from what is there in the 2019. It will continue to be on the same value till 2040. We have not considered any changes in the with respect to the export and import. That is how we have developed these scenarios. And this is the unit operation cost of all the renewable energy scenarios which has been given over here. And for the pessimistic also we have done the same exercise. And now we have considered the capacity utilization factor for each of the thermal, solar and wind based on the scenarios, how much it will be. On the renewable, you can see that by 2040, 2035 and 2040, because of the stacking of the renewable thermal energy sources, the model has shown that there will be a higher renewable energy share which can happen in the thermal energy for the year 2035. And with respect to the wind energy, it is almost like constant for each and every scenario, which varies from 26 to 27, 25 to 27% of the capacity utilization. And also on the solar, it will varies from 18 to 19% of the capacity utilization factor. This was for the baseline scenario, and same thing which we have done for the pessimistic and the optimistic scenarios. And now we have considered for the emissions. Emissions, it's been considered for the thermal generation, how much has happened, how much of the CO2 has been emitted. Those were the things which has been considered. And also on that trade, most of the time, some export import, we have considered most of the times it will be thermal and generation sources only. So that is the reason that we have considered those things also over here, like how much of emission can happen from that generation. And so this is finally the gist of the quantitative and the qualitative analysis of our summary of scenarios. And we can see over here in the emission, KR renewable energy trade, we are having the high emission only because of the
trading aspects has been considered, and the RENCO, though we have the thermal generation, it has been constant, and it is started decreasing because like the more of renewable energy has been added into the system. That means that, and that is the one of the reason that there is a less emission which happened in the renewable energy sources. And also in the capacity addition, we can say that the renewable energy noted, because like only we are going with the 4 generating sources, that is solar, wind, biomass and hydro. And already we know that hydro cannot be added more, only mini hydro power plants can be added. So that is the reason that they, with respect to 3 and matching that dynamic demand for the higher numbers which we have considered, this will be the huge scenarios which need to be taken. That's why there is a high capacity addition in the renewable energy not rate scenario. So with this one, we have also shown in some of the scenario that we have a capacity and the potential to have like to achieve 100% renewable energy sources by 2040. As most of there is no reduction in the unit cost because most of the capacity is added in the 2025, and the renewable energy note rate requires a maximum capacity in nature because of I told that there are only 4 generating sources, and C of almost increases, and we can see that the renewable energy trade scenario 47% is higher than the renewable energy RENCO due to their trading technology which is based on thermal power plants. This is the thing which has been there. Now, yeah.
Last point is saying that your renewable trade scenario is actually causing more emissions
because of the import and export. Import exports are thermal, that is 33.3 and 17.74 terawatt hours, right? So the summation is more. Here in the thermal generation, it is around 8.2. That means the differences are more. That's why there is a more generation which is happening with respect to the thing. We can take some questions, or you want to use right now any of the things.
So
Yes.
we are talking about the CUF for solar and wind plants. Like when you do the analysis for over 10 years, 15 years margin, then there will be some degradation in capacity factor. And
Yeah, we have taken the annual degradation factor of the solar and wind power plant. Yes, please go ahead.
The CUF of wind will vary from location to location.
Yeah.
So, how does it feel? Like some of the capacity has already been allotted to some people, some developers. So, how does this account for that? Because this will most likely choose the best CUF one, no?
Yeah, but the location which has been taken on the wind power plant, that is based on the wind speed. How much of generation is happening?
That places may be already occupied by other developers.
So what you do, you overlap those installed area, you remove that whatever the installed area and whatever the area is there, you calculate that area, and of that area we are using the 10% or whatever the assumption we are doing in the constraint.
Eliminate the existing plan.
Eliminate the existing plan.
Eliminate existing plan, eliminate infeasible areas, like there are some protected zones, eliminate those. So whatever remaining, the average CUF is what is being shown.
And it is taking 10% of the available space.
10% of the available territory.
That user can.
10% can be changed.
Yes.
So this Karnataka, according to your study, it will reach 100% RE by 2040. So what about the load, to meet the load, like regarding battery, no mention in the results regarding battery, because we need battery, no? Storage.
This 100% potential is without battery.
Without battery?
Yeah, without storage.
I have a doubt. So as you said that this 100% renewable energy is without battery, but as you said before, when there is peak demand, you use the thermal power plants to match up the thing. But when we use renewable energy, it's uncertain because you cannot predict its generation. So when we have 100%, how does this model account for?
We use hydropower plant as a flexible resources to overcome that whatever the peak demand is.
It's a 100% renewable energy.
Yeah, because hydro is also renewable.
Yeah.
Do you have a cutoff for each of the renewable energy so it does not go beyond the maximum capacity?
Yes, for the wind it is like 25 meter per second is the maximum wind speed it may have, 5 to 25. So anything wind speed which is on that area is more than 25, we have not considered it.
No, I think you're talking of the generation.
Yeah. So if you are saying I need 1 tera watt of electricity. How much of that, if like 10% of solar, I will not go more than that, you will put a limit or something?
Yes, there are two types of limits.
Okay.
One is based on the available capacity. Say you have 100 megawatt of wind available. So you can generate only say up to 25% of it. So that is one kind of a constraint. Second constraint is how much of renewable you want in the portfolio. Say you want a portfolio with 80% renewable. That will force the model to have 80% renewable.
And have you taken the capacity at 100%, or you have considered a larger capacity and reduce the percentage in terms of utilization?
Utilization is capacity means capacity.
Yeah.
Install capacity. Utilization is with the CUF or PLF whatever.
Okay.
I think this question was the capacity utilization factor. So let's say you have a plant of 100 gigawatt. So percentage, so capacity, it will not operate always at 100 gigawatt.
That's all. So installed capacity is the 100% capacity, and the generation is capacity multiplied by the plant load factor or the CUF.
So that factor you have considered as constant sum factor, right?
Yes.
For each of the
That is different for each technology.
Right.
See, this value of CUF which I have shown is the average annual CUF for an year. That is 8760 data point, not on a point, on a single hour or a single day.
Just curious, in the 2040 model, it's showing wind as the maximum, the factor. Can you tell me why it is taking that?
Wind has been taken because like Karnataka is we have like lot of wind potential compared to the solar.
And also your distribution
with the ground data also.
Okay.
Yeah.
Karnataka has a very high wind potential. Andhra, for example, has higher solar potential.
But it does not consider the factor that it might need a higher capex requirement.
No, cost optimization model. This is the cost minimization of it.
But the landed cost comes more or less the same for solar and wind.
Okay.
So generally for the capacity expansion model, we provide some criteria like projected reserve margin, which is they keep a margin above the
spinning reserve and contingency reserves.
No, that is different. But in the planning stage, if you are forecasting a peak load of about 400 gigawatt in 2030, but you will plan something like 450 gigawatt, you can plan something for the 450 gigawatt. Or you can give a LOLP criteria, like it should be like 1 day in 10 years, that kind of criteria. So in your model, what kind of uncertainty or other planning criteria you consider?
I think what I understood is still it is a deterministic model and you are not considered any.
No. Even in the deterministic model, we give some criteria like a PRM, projected reserve margin.
Reserve margin is
10%
mandated to be say 15% of the peak load. So yeah, I'm not sure if they include it, but it's a single constraint. It's very simple.
But that was not I think seen in the.
As of now, in this study we haven't.
Yeah, because then there is a rating factor. How much capacity credit you want to qualify?
Capacity factor will also come in.
We haven't considered the reserve margin.
There's a capacity credit. So usually reserve margin will come from a firm capacity, but then you want to allow some say wind for the reserve margin as well. So you say 10% is the capacity credit for it. So essentially. So it gets scaled by 1 by 10. It is accounted
that was
for.
my next question. So how you are taking care?
That is I think what the regulator agrees upon. So it's not something. It's an input to the model. It's an input to the model.
In Karnataka model, what is the that
That's more on the operational part rather than the planning part. I feel
It's a planning part.
It is planning part.
As in, it's specified by the regulator or the policy mandate. Those things.
Yeah, but I think currently have we included or
no?
not?
We haven't.
Okay, so just the peak demand and
we have just taken the demand and meeting it.
Yeah, but it's very straightforward. It's a simple, very simple.
Not just the peak demand, hourly demand. The entire demand curve.
In the hourly resolution, you are meeting the demand.
With the respective supply.
And what kind of operational constraint you are putting in terms of operating reserve? Those things you are keeping?
So we don't have reserves. Operational constraint are only the ramp rates we have taken.
Only the ramp rate.
Yeah. Other than that, usually we have spinning reserves.
Right.
Just like you keep a margin of say 5% up and down in both directions. So you keep our operating margin to if there's any contingency, sudden demand rise, so you can accommodate for that.
That can be easily added.
I think thanks Nitin for this point. We will definitely going to add this.
Okay. And for this tool, what is the hydro dispatch strategy of this tool? how it dispatches the hydro?
Based on reservoir levels.
So you are providing the hourly value?
Yeah, we get the hourly value.
Or the monthly value or?
No, reservoir hourly value we
But
get.
what about run of the river plants? Like that's based on the
Mini hydro power plant you are talking about?
Yes. Yeah.
That has been added with respect to with the hydropower plants only.
They both operate on different. You cannot. You should not do that.
No, we should not. But we actually, to be very honest, we did not get much data on that.
That's okay.
So when you get the minimal data, we
Just say we did not consider. Why?
No, for the hydro, so if you are providing the hourly value, so next year it's considering the same flow of the last year?
So the model is interpolating for future years. The same hydro.
How does
No,
it
that's
do
what
that?
we didn't work on run-of-river models.
No, for the ponding.
For the storage, it is like based on rainfall and a lot of things. Like
Okay.
based on historical data, we have
It's
modeled.
following the same 1 year pattern to another year.
Yes.
No, in the reservoir, it operates exactly like a thermal plant. We have water and it's in our hands how much.
Yeah,
we
in
can
practice,
dispatch.
see,
In
what
practice.
you do is, like in a paper as well, so that's what you've done. You use 20 years of data.
Yes. Yes.
What you do is, you get, say from Mara, you have 20 years of data, hourly data, for solar, wind. So essentially, say, you're modeling for, say, 20 weather years, effectively. So you have the variation. It's not the same input in terms of solar, wind, and probably hydro as well. I'm not sure if they've done that. But usually, that's the practice. So you get, say, 20 years of inflow into the river, and you have the pondage size. It's not, say, same from year to year. It's either you could do 1 year, replicate it 20 times, or run one model for 20 years, and every time use a different year.
Okay.
So you can do it both ways.
And then it utilizes the stored energy in optimal way.
It'll either pond it or use to generate electricity based as the requirement in an optimal manner. Yeah, so it'll either keep storing the water to the extent possible, and use it as and when desired. In the
Usually we see that it's dispatches during the peak hours.
Yeah,
Store the
it'll
flow.
dispatch during ramps. I think ramping is what is good at. So, and during that period you'll see, it'll dispatch. Yeah. Even if it's a higher marginal cost. If you plot the marginal cost for, so that's what comes out of ramping. Right? That's how it is different from the merit problem. So although the marginal cost would be higher for a hydro plant, but just because it could ramp faster, so you tend to see it dispatched.
So, is it safer to say that, because I have learned that this is a wraparound the Energy RT tool, is it safer to say that this is the Indian version of Energy RT? Or you have added more extra features or added to that with compared to Energy RT?
No, both are different. Energy RT is just a package being used.
Right. But the Energy RT can do same all these things what we are currently performing, right? And there are already presented results on the US system already. So is it safer to say that this is Indian version, or you have added more extra features?
It is not an Indian version of Energy RT. This is an Indian model which uses Energy RT.
Yeah.
Okay. So what extra? So I mean, out of interest, what extra features you have added? Can you not now? You can put it down that what extra features you have added with compared to Energy RT that would be of a good greater interest.
No, so it's useful to think of it as so Energy RT is a model developer. India is a modeling instance. Energy RT is a modeling framework.
Okay.
So if you supply the particular data, it'll develop an instance.
Okay.
And to the extent why we say it's Indian, because they are actually working on the documentation as we speak. So it's not that it's already been implemented there. So the developer happens to be from US. They're one of the core developers.
Right.
Other than that, the documentation, use cases are being developed as we speak. It's actually not formally launched yet. So that's the contribution. So yeah.
I was under impression that I think US census.
They have done some analysis. So they have built some model.
And similar, I think, capacity expansion. I think those words on the first slide which we are using, renewable REC or capacity, those words are directly matching with.
No, that's generic to the field as such.
All right.
They're generic to the field. So Energy RT is a model generator. Could compare it with say osmosis. Could compare it with times. Could compare it with say plexus. So times is energy system. That's the vision for Energy RT as well.
Okay.
So currently it does only.
Because of capex, right? At one point in your presentation.
Yeah.
So are you? Does that mean, say, we establish this kind of RE, we go for this investment? Next year the capex won't be there. So will the operation cost actually go down next year? Operation cost doesn't depend on capex. Sorry, I mean total cost like. Now there are two ways of looking at it. If you are looking at it from a business angle, you divide the cost across the useful life through depreciation. And for us, we are considering at the first year itself.
From an academic standpoint, it's very easy to say, like, instantly I'll simulate and I'll add this much capacity, but for the real-time basis, it doesn't work like that.
That's why we talk about the limited business decisions will be based on this, but this is not. I mean, we are not prescribe anything at the moment.
This is a reference system.
That will need a lot of more calculations.
This will give you just an idea of like where it is and what is doing the
strategic decisions for that. Long-term strategic decisions.
So, is there any scope like for future work where you actually can see over a longer period of time, do a realistic thing? Maybe that will be of more use to the policymakers, right? Rather than just an academic goal.
That is our goal. So this is how that's why this workshop is going to get the more output of like what all the things need to be added. Where we are having the little bit of like stoppages and that's how we are doing. That's why we do this.
So your model has given the result till 2040, or you have it is there like till...
We can get the result till 2060, but we have stopped it till 2040 from our analysis. Or any number of years, because in the model I have shown you, like you can use the milestone years based on your like I have shown till 2079 also.
Yeah.
So that is how it can be given, but I have stopped it at 2040 on the result basis. So this is just an assumption from our side.
Yeah, so just the one thing that I asked ki, suppose ki, this is like total RE by 2040, it will be in Karnataka, like according to your study, and it is without storage and
without battery storage.
Without battery storage, yeah, without battery storage. And solar is also like very much in the daytime, like India has 5 point something value for like. So is it looking practical that on only wind and hydro Karnataka will survive for like years after 2040?
I mean, the rivers don't dry up yet.
Yeah, but it will dry because the
I had the same thing in mind.
That's why those externalities we can't say. Right?
Imports are also there.
Imports are
only if monsoon fails.
That's
Just one more question on the capex part. So there was an assumption that everything had a life of 10 years. So which
means the storage has 10 years. The storage plant.
Okay,
but it's different for different technologies.
Yeah, but isn't that captured anywhere? Because if we are talking about a 30-year time frame, I have to replace my solar panel and.
So in the morning session, if you remember, we had shown like capacities and net of existing, new, and retired.
Okay.
So we have considered.
Yeah. So initial itself, you will consider that in the capex.
Yes, like we haven't taken the exact years of the existing plan, but we have kind of averaged it.
Okay.
So we have taken off basically operation life of 25 years, as Sanjay has told on that. If we are taking the solar power plant, there is also we have considered the annual degradation factor also in that.
Okay.
So that is also being considered. We have taken both in current.
But if you want to add on more complexity, you can take the model alone. Yes.
So it's just that they are limiting it to those scenarios. If you have more data, and if you want to make it more complex, the model allows it.
True, definitely.
But you are not taken in the case study, maybe because of the data problem, you don't have that level micro or granular data, things like that.
Yeah. Any more questions or?
Yeah. So one question.
Yes,
so for the 20-year horizon, for the 20-year horizon,
yes.
So you solve the case in just one go. You
Yeah.
give the
one
loop
go.
ahead period for 20 years, right?
Yeah, we can go in one go. I showed you in the milestone years, right?
You are not breaking it to 5 years and then.
No, I have broken it into 5 years. 2019, 2025, 2030, 2035, 2040. That milestone years in the chunk I have seen you like repetition of like C.
So
1, 3, 5.
It's making decision for first 5 years. Then
Yeah,
taking
first
the
next
build
5 years.
decision, solving for another 5 years.
5 years.
Okay.
But you can change it according to like whatever, how many years, milestone years you want to. If you want to take it for 1 year also, you can do that. That model gives you the flexibility.
Yeah.
Or if you don't want to see, you can go directly up to 20%.
Yeah, that is also there. It is user specifics.
So I think there's a distinction between horizon and milestone. So you can have a rolling horizon where you look ahead is say 2 years, 5 years, optimize, then take that as boundary condition for the next one. That can be done. And the milestone, other one is say rather than running, because year to year there won't be too much difference. So rather than running for individual say 20 cross 8760, so why not run for say the milestone years only, and for the intervening years you interpolate. So model is running for the duration of so say it's averaging out for the intermediate years. So your the representation of time in the model is 2019 as many number of hours as you want to take, say 8760, or maybe a subset, a representative one. Similar exercise for 2025. So at a time it's then, but there's a loading. So then the intermediate years is just by multiplying a factor. So you're actually running for only those years, milestone years. So you're covering the planning horizon of 20 years by actually running the model for 5 representative years. That's the milestones. Rolling horizon is the other one, say, if you want to say, give a look ahead of 2 years, optimize with that, then take that as boundary condition for the next 2 years. That's probably more correct representation, because that's how the political system operates. They have a horizon of say 5 years at a time. So maybe that works better.
But then you have freedom to choose all these strategies. But you have the freedom to choose all these strategies.
Yeah, you have
can solve the case for 20 years in one go, or with the rolling horizon.
Yeah.
I'm not sure maybe whether it's relevant or not, but usually when we deal with unit commitment, have you dealt with unit commitment in any? No, right? Okay, because I was curious that you handle this problem in a linear fashion, linear program.
Yeah, linear LP model.
So, okay, but because not unit commitment, otherwise I was wondering that how you handle it in the mixed integer, because the results you're comparing, again I am still stuck at that slide. Anyway, we can have offline conversation.
We haven't considered the number of plans.
So you need dispatch. You use that word dispatch. So, okay.
Okay. No, it is basically a short-term outlook at the whole problem.
All right.
See, here this is a planning problem. So the equations might remain same because your time thing and adding more variables. Instead of technologies, you make it units.
That's true, but
and add some integer restrictions.
That's
so
true.
That will make your life whole really complicated.
People are handling with non-linear also. Mixed integer is still easy to.
No. Yes, I agree. See, that is the fancy of modelers.
Right.
But practitioners, they want simple, implementable solutions, easy to understand. Okay. So we need to, personally I would believe 90% accurate is enough for our lifetime. From 90 to 95%, the life becomes really tough. 95 to 99, it is like astrological prediction.
But then when at the same time we are making...
I will completely agree to that.
Yeah.
At the same time...
90 is good enough, even in industrial scenario, to work with practice.
Yeah, it is extremely difficult, to manage
with the complex model, complex
just politely arguing with that on that point.
No, I agree. No. We have also gone through that process.
Right.
And at the end, the linearity assumption is comfortable for
I totally agree.
all those errors.
I'm fine working with linear, of course, no one would like to go there. But when we are making a strong statements like complete renewable operation, I think that requires us to go on that 10% zone where we are not comfortable.
There is another scenario where we don't have resources after 2060 or 2070, and entirely we are depending on renewables. So we got to understand the renewable better than to think on that particular date. So if you plan today, maybe we can manage the things 2070.
Makes sense.
The second thing, you can create a subsystem. The data which goes into that subsystem become more deterministic. The uncertainties are involved with your weather, the demand. That is basically the external inputs to the model. That I think you can do it externally with whatever the complications that you want.
No, I totally appreciate the way you handle this problem.
I am not telling. This is basically we need to change our mindset, not only here.
Okay.
In the modeling world itself. If we go behind the accuracy, you know, I always argue, any predictions done by IPCC, very rarely, we compare 10 years back what they did and now. Even at that 2010, what they claim is most accurate, is very comprehensive, we have captured all the factors under the sun and we have predicted. But compare now, are they comparable? I think the trajectory itself, that's when they came out with the what you say, the wide range of optimistic to pessimistic. And whoever is within that range feels safe. The range is huge. See, I think we need to change our mindset. Model the known things.
All of us in that sense. I mean, all customers.
All of us. Live with the known things.
Right. That makes life easier. I agree.
No, but even if it predicts by 2040 and even if we can achieve by 2050, we all should be more than happy.
No, we are planning for 2040. Let's be happy when we achieve it at 2040.
No,
very well accepted, but we know how it works.
Otherwise, what's the point of planning? Then let it be. We will be happy at 2050. There is no point of planning.
The catch is it's better the way you
If
were
we say 2040, at least by 2050 it will be ready.
No.
Taking it once
But this approximate roadmap is important.
Totally
Because
agree.
investment decisions.
I agree with that.
Because otherwise, if we don't add capacities now, we will not have anything.
That's just
I think that is, I don't think any model would have predicted the downward trend of Adani shares. No model.
There is no mechanism for that, yeah.
It's an unknown.
Yeah, thanks for
No, he did not use any model.
Okay, guys, thank you everyone. Let's catch hold of high tea now. We'll break for tea. We'll meet at 4 o'clock for the round table session. Thank you all. So we'll end our session right now. On our modeling, we will be. If anything is there, you can contact us offline.
Good evening. I hope all of you had a good tea. I request all of you to take a seat. I hope you've noticed that there's been a change in the orientation of the seats. This is because we are going to the next phase of the workshop, which is going to be a roundtable discussion. So we've selected 5 topics based on the expertise of the people who have elected to come for this workshop. So that we can have some group discussion for about half an hour and then have a short presentation from each group based on the discussion that they have with the moderators from our lab. Okay, so I'll first give you the general topics, those 5 topics that we've decided on that are going to be discussed today, and then I'll tell you who is going to moderate them from our lab. And then we've already segregated all of you into 5 groups. I'll call out each name by group, and then your moderator will call you wherever they are, so that all of you can sit together and then start your group discussion. Okay? So the topics are as follows. So the first topic is application of energy models in industries, challenges and expectations. This will be moderated by Ms. Disha. The second topic is relevance of carbon neutrality studies and assessments. This will be moderated by Mr. Manjunath. The third topic is potential for ESG assessments through IDEEA. This will be moderated by Mr. Gautam. The fourth topic is integration of policy and governance in open source energy models. This will be moderated by Dr. Tarun. Right. And the last topic is roadmap for SDGs, contribution from energy system transition. This will be moderated by Ms. Anushaya. All right. So now I will call out group 1. As I mentioned, we have already put you in different groups. So as I call out your name, please go to your respective moderator and then you can start your discussion. You can just go there, they'll tell you where to sit, yeah. So for group 1, Anand Madhu, I am sorry if I mispronounce your name. Shreya Mehta, Sara Khan, Nitish Kumar, and Sudarshan R. Disha, I already mentioned. Group 1 moderator is Miss Disha. Yeah. I think Samrid, you can help them out. Okay. Group 2 will be composed of Arun Kumar M, Shripati Anirudh, Vaisak Suresh Kumar, Swapnil Soni, Satish Kumar. He's left. Okay. Yeah, that's all for group 2. Group 3 will be Group 3 is Group 2 moderator is Mr. Manjunath. He's sitting here. Group 3 will be Prakash Thanki, Vignesh NV, Tejaswini GV, Ashish Chopra, and Chirag Ramesh. So your moderator is Mr. Gautam. Gautam is here. Okay. Group 4 will be Upasna Ranjan, Sachin Yadav, Rashmi Shenoy, Rohan P. Uni, and C. Gajaraj. Yeah, you can sit there. Group 4 with Dr. Tarun there. He's your moderator. Finally, Group 5 will be Avinash Sharma, Raj Raviraj Singh, Shreyas Malia, and Vikram N. Yeah. So you please gather around Miss Anushya. So as I mentioned, each group will have around 30 minutes to discuss among themselves the topic that they have been given, and then the group can elect one nominee, one spokesperson to come on stage after the half an hour to generally summarize on what they have discussed and to generally describe their discussions that they have taken place. Okay. Is
your name Astha Pariwal for a 5th group?
Astha Pariwal? Yeah, 5th group. Okay. Is there anyone else who is left out by any chance? No? Okay. All right. Sure.
What effect this energy transition can have on this SDGs? Because we all know about SDGs, right? Because I think we are all from sustainability background more or less. And then basically I had certain thought of mine which I want to just give in 2 lines maybe. So it's like this SDGs are intertwined with each other. So you touch one and all other things gets affected, right? So in my domain, because I work with energy, we know that still 770 million people don't have electricity, even though we say that universal access is SDG 7, right? Affordable and clean energy for all. Still, we haven't reached any capacity to how other so you face these issues global warming or something like that, which harms trees or 13 or other things.
Currently, I'm working as assistant professor in the chemistry process in biology. Opposite to whatever this domain is. So I work with food technology, bioprocess engineering, design, and
probability will get accepted. So basically, we will make patterns, which is very important. Exactly this. Just seriously be part
they are willing to pay that much to go green, and they are also much well aware of things like child labor and all that. So they know that only because it has used so.
I'm Sudarshan. I am an assistant CST, IISc, and I'm currently working on solar panels recycling. Which technique is better suited for
So I'm working on a preliminary commitment model based on this.
Your name was there.
Yeah, your name was called.
But somebody has to take notes.
All groups, I would request you to start summarizing the discussions you've had till now. So in a couple of minutes, we'll start with the summary. Please select a spokesperson amongst your own group and then give me their names. All right, everyone. We'll start with the summary presentation from each of the group. I think we'll start with the presentations, everyone. Yeah, 5-10 more minutes.
So 5 minutes, not 10.
5 minutes. Okay, fine. You can take 5 more minutes. Please remember that to keep your summary to less than 5 minutes. 5 minutes would be ideal time. Right, everyone. We'll start with the summarization. So from group 1, I like to call Mr. Sudarshan to come on stage and give a brief summary about the topic that they have discussed.
Yeah, good evening, everybody. I'm Sudarshan from Group 1, and I shall be giving for the next 5 minutes a very brief summary of the discussion, the very eloquent and vigorous discussion that we had, and from Disha's group. So our topic is application of energy models in industries, what the challenges and expectations are. So first of all, what are the problems that we are facing with our own software that we use in our work. So for example, we have our open sources and third-party and in-house softwares. So we are discussing how each one of these categories is advantageous over the other. So open source, of course, it is available to everybody, but then again, there are constraints of the rigidity of the model. So the models that are present in the open sources, or sometimes though it may be documented, it is very hard for people who use it on a day-to-day basis to infer what the actual implications of it are. For example, she was saying of an example in her own project where there were some waves in MATLAB, whereas in another commercial software they had snubbed it and they were showing only a small, there's only one data point over there, a smooth data curve. So such discrepancies may cause blockages in our own research fields. The second thing is availability of data. So when we are using open sources, I mean, there's always a limitation of how much data in a particular region of study is available. So we usually rely on foreign databases, and not much is present in our own Indian context, hence making our Indian models quite irrelevant by using foreign data points. The next point is when we are projecting, we're making a prediction or a projection, what time horizon are we to consider? So how does considering a very large time frame or a large horizon affecting our own research or answering our data questions, our research questions? So like we all know, there is always a compromise between accuracy and impact. So the longer time frame that we use for making a prediction, the greater, so to speak, emotional or ethical impact it has on the people that who is the audience of the research paper. So, for example, if I'm making a prediction of that there'll be a 12 billion population by the end of 2040. So, whether it's going to actually happen or not is irrelevant to the in a certain perspective, because it will help make some policy recommendations. And so, accuracy is one thing, and the impact of the prediction is another. And we also have been joking about how government data, is sometimes very unreliable, because there are some additional rows which get incorporated into data sheets when it's in totally unexpected places. So that is another problem. And of course, there's always a problem of confirmation bias and how we have to tweak our own models to suit the data which is available. More than using a model and testing it with the data available, we have to manipulate, and manipulate is a bad term, but change or tweak our models to suit the data available. So that is a very sorry state of affairs. And also, we have been discussing how during transitions, so for example, when the decarbonization of thermal plants has to happen in some rural parts, there are many livelihoods which are affected, because they also have been employed in such industries. So although environmentally it may not be very sound, they should also be even economically, and there should also be a social perspective to it, and to consider what a sustainable solution is going to be. Finally, relying on RTI to procure data is quite a horrendous thing to do, because we know how the government, how quickly the government acts on all of these, and it may in fact, make a hindrance to our own research in such circumstances. And finally, the government must take measures to educate whoever is getting affected by a certain policy decision, and also make data open.
Thank you, Mr. Vaishak, for that even more impressive summary. Puts more pressure on Group 3. And thank you, Manjunath, for moderating that discussion. I would now like to call Mr. Prakash from Group 3 to come and give a summary of their
fifth also. So we will take it as a more optimistic way, and considering we got applications of ESG, might be you all aware that nowadays all the sustainability department comes from like transition phase from liability to assets, right? Earlier they considered it as a liability department, but now people are considering it as a asset department, because of the force of investment and investors forcing all the companies to disclose all the environment, social and governance aspects of the companies for the climate change and for the people, and how they are doing it for the betterment of the people and global citizens and the company, right? So we wanted to evaluate, our team has evaluated that this particular software might be utilizing the many data point which be captured or the required under the ESG, particularly environmental part will be more efficiently covered in the IDEEA software, that because majority of the data like energy related, climate change related, and how the energy is utilized, how that emissions has been emitted because of selections of the different technology or the energy generation technology. For example, sometimes I used to call one statement in all my environmental presentations that people are saying that we wanted to reduce our carbon dioxide by certain numbers, right? There, if we see that number will be very high. For example, if we consider the mass balance of carbon dioxide, that C is 10 for 12, O is 10 for 32, and CO2 will be 10 for 44. So wanted to reduce the 44 tons of CO2, we don't need to reduce actual 44 tons of CO2. We just need to reduce the 12 tons of carbon which is present in the fuel. So it will be make more psychological statement, and communication is much more required. So this kind of data can be captured with the technology and selections of the different energy technology. We will showcase the carbon emissions of that technology, and people or the user of this software might be use the better decisions that which technology combinations we required to fulfillment of our carbon targets and commitments. Likewise, same other social and governance part, it is more towards the qualitative statements. what is the customers or the employee engagement there, right? How many complaints are there against the company's product? How many like tax they have filed on the time? Or is there any breaching of the GST or any other taxes are there or not? So that kind of things matter for the company's transparency of the data. If we rightly said that no one will predict the biggest company in India wanted a downfall will come, right? Only the one person has make the difference by stating the what is the wrong practice is happening, right? So that kind of transparency is not there in your operations, and you're not following the ethics and morals for the longer run. That company is not going to be run or the sustained for long time. If we wanted to run the company for centuries, we required more like moral and ethical practice for that, right? For the on the people, it should be impacted. Then only it will be possible. Thank you. Thank you very much.
Thank you, Mr. Prakash, for that very insightful summary. Now I'm eager to see how Group 4, how they add to this entire discussion. So I would like to, before that, I would like to thank Gautam for moderating that discussion. So from now Group 4, I would like to ask Ms. Upasana to come and give a summary of their topic.
Yeah, hi everyone. My condition was same as Basak. Like it was somebody came and who is presenting, and we were like in the introduction part only. So our topic was integration of policy and governance in open source models. So actually from morning we are dealing with models only, like what model does, what are the inputs, how the constraints are there so that they alter the model. So basically actually it's firstly if we talk in terms of the government, then government sets some targets. So suppose 2070 net zero is one target, and then government prepare one roadmap like how we should achieve this target. But sometime in our government, whatever the things we are seeing, this roadmap is missing. So because of this roadmap, we are always end up doing something else, getting some bad results. So I think this modeling is energy modeling or any modeling is a good idea to implement. Firstly to prepare that roadmap, and whatever the government policies are there, then that should be incorporated. Suppose the power sector modeling if we are doing, then this new RPO or some increase of BCD, or there are many policies are coming. So when we get the results, when we put the government policies, so we get the real results. Ki, okay, if BCD has increased to 40%, so my domestic manufacturing is not going to boost in coming years. So I need to find some other way. And also, if it is open source, then suppose they have presented the Karnataka model. If it is open source, then I put the results of Jharkhand or Bihar, and then I'll see ki, okay, what the government policies of Jharkhand for RE, or they have some constraint regarding that. So I can put that into the model, and I can see ki, okay, when is the year I can be 100% RE, or is it possible for or not? Should I import, export? All these things could can be we can get the results just because the model is there and we are incorporating the policies and governance. So I think it's very much required, and yeah, this give a good idea of how to follow the roadmap to achieve a certain target. Yeah, thank you.
Thank you, Ms. Upasana, for that excellent summary. Of course, and Dr. Tarun for moderating that discussion. Now, of course, we've left the best group for the last. So I would like to call Ms. Asta on stage to give summary of their topic.
Good evening, everyone. The topic for our group was Roadmap for SDGs, Contributions from Energy System Transition. We'll talk about this entire thing from Indian scenario, and when we move in that direction, let's try to embrace two things. India as a landscape is very diverse in two terms. In terms of the geographic and the environmental conditions, and second, also in terms of the growth rates of different areas. So with these two things in mind, and basing the entire strategy on the three pillars of sustainability, which is economics, social development and environment, the roadmap we think that will make most sense to move forward in would be a step increase. So when I say step increase, it will move parallelly from one point as a decentralized approach, and on the second, the entire projections for the nation to grow as a one unit. So we'll talk about first the decentralized approach. In the decentralized approach, it can be bifurcated into two directions. One, decentralization of the technology. Second, the decentralization of the data. So what I mean by that is, when we start to formulate models, let's also see what in a particular area, what is the energy requirement, because the energy requirement of, for example, an agricultural intensive land will be different from an urban area. So it's not probably wise for us to just generalize that and use that for deciding which technology will make sense. So let's have first identified what is the bare minimum energy that a particular area needs to not be limited in terms of energy requirements to move forward in terms of growth. See what is the available resources that can meet that energy target. So that will take care of our current energy needs, have faster implementation, and will at least lead that particular area in terms of growth. So the lag period will be taken care of, and then the second approach will come towards the scale up. So in that, the models can have, if we bridge that gap, what is the growth rate with which that particular area would be growing, and when that happens, what will be the increased energy requirements of that area, and how can we supplement that, so that the energy that we are producing and the routes that we are choosing to move forward do not overestimate the energy needs, do not lead to wastage, and are moving in tandem with the growth rates that a particular area can afford and sustainably move forward in. And in doing that, so the idea is to move towards self-sufficiency, respect the biodiversity that exists, be more inclusive of it, and in building the technology also focus on skill transfer involving the local population, so that the self-reliance of the community in terms of energy adaptation and also taking the technology forward is also built at the ground level and takes the community forward from that perspective. Thank you.
Thank you, Ms. Asta, for that summary, and Anushya for moderating that group. Now we are almost towards the end of our workshop. So for concluding remarks and comments on future directions, I would like to ask Mr. Mithivachan Hiremath to come on stage and give those remarks. So Mr. Mithivachan Hiremath is the co-founder and director of SusPoT-Center for Sustainability, a think and do tank based out of Bengaluru. Some of the international organizations wherein he has worked before founding SusPoT include the German Aerospace Center, Wuppertal Institute, and the United Nations Climate Change Secretariat in Germany. Mr. Mithivachan's work in the field of energy and sustainability has been acknowledged by various national and international awards, including the Alexander von Humboldt Climate Fellowship for Prospective Leaders from the German Environment Ministry. Recently, he has been appointed as a member of the Technical Advisory Group at Science Based Targets Initiative. So I would like you to take over, Mr.
Thank you, Rahul, for a introduction. Is it good? Can you hear me? Yeah. Good evening, everyone. So we from SusPoT-Center for Sustainability, I think we'll be basically sharing some last and future direction to this workshop. So I hope you have some energy left. It's been a busy day. We'll wait for the presentation to start. Let's get started. Yeah, so basically before going into the winding up session, just a quick intro about SusPoT-Center for Sustainability. We basically started with the objective to assist diverse stakeholders, be it government, decision makers at all levels, in helping them to become carbon neutral. So So that is the that has been the focus, and we operate in two different verticals. One is which we call under think tank, wherein we basically work on research, policy, and things like that, and on the other, which is a do tank, which we call, wherein we engage with the consultancies and also some of the groundwork with farmers, for example, things like that. So as a think tank, basically we as a startup specialize in integrating life cycle thinking, big data analytics, and system dynamics, and also to how to integrate these and make them sustainable strategies, okay, for the decision makers to act across all levels. That is where our specialization is. And we were in the initial years we were incubated by Shakti Sustainable Energy Foundation and Indian School of Business. So our expertise basically falls in three domains. One is we specialize in circular economy and critical materials based research and studies based on life cycle assessments and things like that. And also we specialize in developing open source platforms and also modeling using R, Python, GAMS, various other tool set. So and moreover, I would say we have done and also we intend to engage more on the third aspect, which is new technological intervention and how do we benchmark them in Indian context, given that most of the technologies are developed somewhere else and coming to India. So we specialize in benchmarking them in Indian context from various indicator point of views. So on the do tank side, we engage with the industries in particular. I'm highlighting only the industry part. We also engage with farmers. I'm not touching that. So wherein we work on various stakeholders and clients, wherein the idea is to assist them in ESG consulting, basically focusing on life cycle modeling or supply chain greening, GHG inventarization, net zero strategies, and things alike. So these are some of the policy brief papers which we published in just last 1 or 2 years, and the first study is about the electricity transition roadmaps, which I would like to highlight because this study can act as a prelude to today's workshop, wherein the idea why we started that project with Shakti at that time was, see, when it comes to modeling and also the roadmaps, you know, every organization in India, at least, although there are few in number, I would say compared to Germany or USA, but every organization has their own roadmap, okay, but India is one country. So the decision maker would say which one I should follow or which one I should not, or what are the pros and cons of different roadmaps. So we thought it's a good idea to compare all the at least prominent roadmaps available in Indian context from multiple angles, okay, because often roadmaps are developed only with on 1 or 2 optimization point of view, let's say economics or GHG mitigation now, okay, but what about the water footprint, for example, or the land footprint, or some others, job security, for example, things like that. So that was the attempt. So, and these are some of the major collaborators partners we are presently engaged with. And now I come to the main content, okay. I just want all of you to quickly take your phone and scan this image. So basically it will take you to 4 questions step by step, and wherein I want your feedback. So this kind of, and also my colleague Jishan would be assisting me in that. Yeah. Did everybody logged in using the scanner? If anybody has issues, let me know.
Open the link.
Yeah, just you can use your camera. Yeah, open the link. Yeah, it will start now. Yeah, you can start now. Yeah. Yeah, if you are at the link, then we'll start the questionnaire. I think Jishan, we can come back to the. So you see the questions on your screen? Yeah, go back to the scanner a bit again. Okay. People who are still have to scan, please scan the image. Your camera should catch and then you have to click on the link basically. Okay, sure, that's good. Okay, basically the first question is, I mean, according to you, I mean, there would be series of challenges. What do you think the first most and foremost challenge for a open source model, you know, I mean, especially in the Indian context. So you can share this screen. Results. I think still 2 or 3 people have to fill out, so you can see which one people are choosing. So most of them opt for data availability.
Global campaign going on open data.
Yeah. Yeah, certainly data data availability is certainly a major issue, especially.
Rephrase that question to reliable data.
Okay. Yeah.
Data you get.
No, but even I would say from modeling point of view, still there are many gray areas wherein you don't get data. You are right, once we get the data, then next question is how reliable is the data, but I am still not sure whether we are there, to be honest. Okay, so basically I think, yeah, most of you say data availability is the issue, and also skilled human power third, and second is lack of support program. Yeah. So basically as an IDEA model as such, I would say we would be focusing on second and third part mainly. But data availability is one thing which I would say need action from diverse set of actors. So basically I would say the second and third, if it starts getting through, then the pressure on the other regulatory bodies, be it, I mean, most of the data coming from, especially governance data coming from government repositories and all, we need a critical mass and ecosystem to be built up, so to make the data available. So yeah, thank you. So next question. Show the question. Yeah, so next question is, how do you like to use IDEA model? I mean, in your respective field. Just, I mean, imagine you know the model, or based on whatever basic preliminary exposure you have got. It's very basic. So how do you like to use? It's just a, I mean.
Why only one choice?
Sorry?
Why only one choice? I mean, it allows us to just.
Yeah, but we wanted you to be clear, you know. Because in the end, no, everything is required. See, all the, even in election, there would be many people. You might like 2, but you have to vote only once, right? So that.
Is it that only?
But that doesn't mean that that is the. But that doesn't mean that that is the only point. I totally agree that. But you should be clear. At least you prioritize accordingly. We want your priority. Okay, so we see more on net zero strategies, and also industrial energy management, and also maybe because of the stakeholders today from more on industry side. But this is certainly one of the thing we would be working on. Maybe I would be highlighting that in the next slide, how we are planning to, or at least it is in our planning process to customize further the IDEA model for the industry audience, because today the focus was mainly on regional energy planning and more on the planning side. Yeah, next one. Okay, the third question is, part of our idea is also to understand, I mean, if one is open source modeling community to happen in India, and also to get it more support, and also to have more skilled human power working in this direction. So what kind of training program you would like to have? I mean, if given an opportunity or option, you would like to have more offline, online, semi-mixed, hybrid? It need not be just with IDEA, any modeling, any other open modeling. So what would be your preference in general? Yeah, you can start. Okay. So many people would like to have it very brief, 2 to 3 days of offline, then done with it. No daily or weekly. Okay. But still, the weekly things is also lucrative compared to the last one. Monthly, no. I think we already moved out of that age of months. Weeks are already too much. Okay, this is the final one. So these are just random, I would say, kind of ideas, I would say conceptual ideas. So it doesn't mean that we will be doing this anytime soon, or these are very much in the planning process. So I would say if you want to make IDEA model to be more usable, what kind of future customization you would be interested in? Okay. So maybe you would like to contribute there, or you would like have that customization, then after that you might start using it, things like that. So keep that in mind and just quickly. Okay, obvious, right? Obvious. Yeah. So we need GUI. So I was also telling Varun, so earlier the other day, so GUI is kind of a must. Even. And also optimization for industrial use. Okay, so I think that is we thought of taking some quick feedback from you, but I think Varun and his team might be sending you a feedback form by email. I do request all of you to take 10 minutes or whatever it is to fill it. I hope you all will fill it. So Varun. Okay, so just to sum up, see, I mean, one thing I thought I should emphasize again at the end of the workshop is, see, what is presented today can be said in three ways, or three things. Okay, one, what is presented is a basic model, skeleton of it. Okay, that is one. Part two is, and some of the scenarios, results, assumptions showed is what the team did using that basic version. It doesn't mean that the model presently can do only that. Say if I do this, I use the same model, I can go for different assumptions, different data sets, I can go for high granularity, that the present model still allows it. Okay, so but the team did not do, they just presented what they did it. Okay, that is the second thing. The third thing is, this doesn't mean that the model is already everything is done. There are too much things to be done in the model, and here is where we would like to highlight and emphasize, and we need all of your support and also the support across the country, because these development of open source, when we say open source, open access, it doesn't mean that one institute or organization or a team does it and then they are responsible for it. If that is the case, then it is not open source or open access, then it is a proprietary model. You fund and that organization is responsible. You will tell, okay, if you have any complaint, you will say this is not good, you will go for something else. But that is not the open source philosophy, right? So if that is the thing, then I would say we are already not looking at open source in a proper way. The open source is, we develop something, okay, and other people in the ecosystem think something else can be added. They should add it. And the point is, we allow them to add. Okay, that is where the thing is. Okay, but most of the proprietary models, they don't allow you. Okay, they want to control it. But here the beauty of it is, we make it flexible, we keep it open, so that if tomorrow some industrial player wants to add something, he can make it. If somebody wants to have highly granular data set and he has access to it and he wants to model it, or he wants to run different kinds of optimization, not just economics, even also life cycle, whatever it is, it should be possible to do it. Or somebody thinks the model is not at all good for him, he wants to restructure it. Okay, welcome. So this is the model we have built it, use it. Instead of reinventing the wheel, build upon it and do it and again share it. So that is how the open source community grows. Okay, but these are the things which are basic, especially for some of us, because we are part of the European energy modeling community as well. But in India, I would say, to be honest, we are still very far, because we don't understand, the ecosystem doesn't understand it, okay, because of various reasons. So the idea of the whole team here is, how can we develop that ecosystem? Okay. Towards that, I would say basically there are three things we are planning, three future directions. One is, as I said, we would like to make it open access, and we would like to develop the IDEA model further in that direction. For that, we would be very much interested in collaborating and also develop add-ons or customized packages depending on the clients or even the other partners. Okay, but this is a thing which other partners should come in. So maybe we are happy to engage with them, discuss how can we help them and things like that. So this is something wherein we need support and collaboration. So if any of your organizations or in your network looking for it, then feel free to get back to us. Okay, that is one. Second is capacity building. As I said, we would be slowly coming up with more structured programs on modeling as such, and also the IDEA model and also other kind of modeling related programs. And we would be happy to update you, and you would be first part of the email chain, or I would say newsletter. You would be we will be kept updated about that. So On that, we will be offering various online and offline training programs. That is 2, so that we can have at least build a skilled human resource, okay, over a period of time. And the third is open source ecosystem or community development in India, which I already touched. This, I think, this is very much important, because unlike proprietary models or the top-down models, where there is a funder, your organization did it, and somebody in the government, he trusts you, and you say, then that is it. That is the traditional way, okay, or top-down way. But here now the situation is not that. When we say open source, it's about involving more people, more community, making things transparent, many other things, okay. But for this to happen, we need at least a critical number of modelers, researchers, even the public who understands this, okay. Without community, open source cannot sustain. So that is the basic rule. Even when you see the computer programs and open source community in the computer ecosystem as well, you need a critical mass, okay, because it has to come from the bottom up. It is kind of questioning the whole tradition, that has come in a different way, and here it's coming up in a different way. So that is why I think this is where we would be focusing as well, so that it's not just about IDEA model. Maybe some people might have done some other model, okay, but the idea is to bring together in a platform, okay, so that we can have meaningful exchanges, okay, and also what kind of support we would like to give to them from our side, or some of the best institutions in the country working in that direction. So these are the 3 future direction we would be very much interested in taking further. So any of you or all of you in your network interested in any of these, feel free to get back to us, and we can schedule a call and take it further as well. So I would say that is it for timing. If you have any feedback, you are totally welcome. Thank you. Have a nice day.
I would now like to ask Dr. Balachandra Patil to please come on stage to award the certificates for all the participants today.
Rather than an official requirement, it's a memory. Having spent one day at IISc,
yeah.
I think it is a memory for all of you. Maybe some photos also you will be sharing, no?
Yes, we'll be sharing photos.
Yeah.
So I would like to start the awarding of the certificate by awarding Ms. Lavanya Padi from the Environmental Defense Fund for not only her enthusiastic participation in the workshop, but also being a driving force behind it. So for that reason, I think she gets 2 certificates.
She's also kind of a troublemaker for she wants everyone to work.
Mr. Vaishak Suresh Kumar. As I call your name, please come on stage. Ms. Asta Pariwal. Mr. Arun Kumar M. Mr. Arun Kumar M. Mr. Ashish Chopra. Mr. Avinash Sharma. Mr. Kaushal Joshi. Mr. Nitish Kumar. Mr. Nitish Kumar.
Lavanya, you would like to give some more certificates?
Lavanya, would you like to give the certificates? Mr.
Yeah, Tarun, we can ask.
Tarun, Ms. Tejaswini. Ms. Upasna Ranjan. Mr. Vikram N. Mr. C. Gajraj. Dr. Rashmi Shenoy. Mr. Rohan P. Uni. Mr. Rohan, I think he's also. Mr. Anand Madhu. Mr. Sudarshan. Yeah. Mr. Vignesh NV. Finally, we would like to give a certificate of appreciation to Dr. Tarun Sharma. Thank you, everyone. I would now like to ask Mr. Varun to come and give the final vote of thanks.
Hello, everyone. First of all, thank you all, and thank you, Rahul, for this wonderful introduction. And first, I will extend my heartfelt appreciation to all the participants whose support and presence made this event a great success. Now I would like to express my deep appreciation to Dr. Balchandra Patil, our mentor, who not only granted us the opportunity to present the IDEEA model to such esteemed participants, but also provided us the complete freedom and guidance during these tricky situations. Honestly speaking, we are very much indeed fortunate to have such a great exceptional professor who supported us unconditionally. It is very much rare to see in the whole IISc after this 10 years of career. Thank you, sir. Now I would like to extend my gratitude to Partha Bosu and Lavanya Padi from Environmental Defense Fund for their unwavering support and encouragement throughout the event. Special recognition goes to SusPoT, Mitavachan and Zishan for their concluding remarks and designing the whole banner, poster and the event. I would like to apologize to Zishan because I eated his head like anything to make this whole process very much. And now I would like to additionally thank Dr. Tarun Sharma for his opening remarks, and he's been the backbone of us for standing on whatever might be the questions. He's been there with us and also on moderating the session. Now I would like to commend the moderators Disha, Ansuya, Gautam, Manjunath for their excellent conduct of roundtable sessions. Thank you all. Now I thank our MC Rahul, who did an outstanding job and deserves recognition for his contribution. Thank you, Rahul. Now I would like to thank all the volunteers who helped us during this event, especially from the Masters guys, Devdarsh, Romsha, Avinash Singh, Nikita, Anirudh and Gavini Lokesh for their tireless efforts to make this event a great success. Thank you, guys.
now, last but not the least, I would take this honor to acknowledge my unwavering support of my colleagues Abhishek Das and Samrit Sharma, who worked tirelessly with me almost like 2 months for 12 hours a day to present this idea model, and lot of brainstorming sessions from morning till night. So their dedication and hard work were invaluable, and I cannot thank them enough. Thank you guys for always being with us. Now I really look forward for all of you guys in seeing in all the upcoming events. Thank you all. This is Varun Jyoti Prakash signing you off for the day. Thank you.
Thank you.